In a universe that begins almost perfectly smooth, a single spark sets everything in motion. Space unfolds, time finds an arrow, and whispers of quantum noise grow into galaxies. Tonight we trace that mystery from first light to the deepest questions why there is something rather than nothing, and what if anything lit the fuse. If this journey into cosmic origins intrigues you, please like the video, subscribe for more science storytelling, and turn on notifications. Share your theories in the comments. The oldest light in the universe arrives as a near-uniform glow that pours from every direction, and with patient attention it becomes a map rather than a backdrop. He observes it as the cosmic microwave background, a relic from when the hot plasma of the early universe cools enough for atoms to capture electrons and allow light to travel freely only a few 100,000 years after the beginning. That light stretches with expanding space and sinks into long wavelengths, but it keeps the memory of the last scattering surface as faint temperature ripples and delicate patterns of polarization. A century of radio receivers and cryogenic detectors turns the sky into a sphere of clues. A spacecraft from the National Aeronautics and Space Administration named the Cosmic Background Explorer first announces a nearly perfect blackbody spectrum and hints of tiny variations. The Wilkinson microwave anisotropy probe sharpens the picture and delivers the first precise cartography of the infant cosmos. The Planck mission from the European Space Agency renders the texture with still finer detail, and ground-based instruments at high plateaus and polar deserts such as the Atacama Cosmology Telescope, the South Pole Telescope, and the BICEP and Keck arrays layer new frequency channels and deeper integrations upon the same ancient canvas. What looks like a smooth wash resolves into a mottled pattern, only a few parts in 100,000 above or below the average temperature, and inside those tiny deviations he reads a whole inventory of the universe. The pattern follows the physics of sound. In the primordial plasma, photons push out while gravity pulls in, and the contest sets up acoustic waves that compress and rarefy matter and light together. When the fog clears and the light decouples, the waves freeze into rings of hotter and colder patches whose characteristic scales appear as a sequence of peaks in the statistical distribution of the map. The relative heights and positions of those peaks report the contents and geometry of the cosmos. A dominant first peak tells him space is nearly flat on the larger scales. The ratio of the first to the second and third peaks whispers the fractions of ordinary matter and unseen dark matter. A late time smoothing from gravitational lensing hints at the clumpiness of structure that grows long after the first light is released. Even the faint curl-free polarization pattern, born when the last scattering imprints a direction onto the light, helps fix the moment when the fog lifts, and how the subsequent era of the first stars reionizes hydrogen and scatters a small fraction of the glow again. One map becomes many measurements, and many measurements narrow the story into a consistent framework. The age of the universe settles near 13 4/5 billion years. The inventory prefers mostly dark energy, with a lesser share of dark matter, and a modest slice of baryons that build stars, planets, and people. The initial conditions prefer a nearly scale-free spectrum of fluctuations, tilted only slightly, so that larger ripples carry a touch more power than smaller ones. The whole picture looks deceptively simple, and it is this simplicity that deepens the mystery. The sky is almost the same temperature in opposite directions, although those regions could not have exchanged light or information by the time the background is released. The uniformity points to an episode that forces distant patches into early contact, yet the map alone does not dictate which mechanism does the job. It merely insists on coherence where none should be easy. The data promise clarity and offer anomalies in the same breath. On the largest angular scales, the power dips below naive expectation, and the broadest modes appear to share an orientation that tempts some to sketch a cosmic axis. A conspicuously cold region in the southern sky stirs questions about its origin. Is it a mere statistical fluke within the allowed randomness, a chance void along the line of sight that empties matter and cools the beam by gravitational redshift, or the faint scar of new physics that bends space in a way not yet captured by the prevailing model? Polarization adds another layer. The gradient-like pattern tracks the same acoustic physics that patterns the temperature, but a curl-like pattern could preserve the ghost of gravitational waves from the first instance. He follows the careful choreography of teams that chase that subtle swirl while they subtract the glow of galactic dust and the crackle of synchrotron radiation that pretends to be cosmology. Limits tighten, claims are revised, and the community learns to treat discovery as a ladder with many rungs rather than a single leap. What survives the tests is folded back into the map, making it both cleaner and stranger. Gravitational lensing then bends the story again, literally and figuratively. As ancient photons cross the web of galaxies and dark matter, their paths deflect and the small-scale features smear. The lensing signature can be reconstructed, and the result is a sketch of the later cosmic scaffolding drawn by the light of the first fire. Those reconstructions agree with surveys of galaxies and weak lensing of distant shapes seen by optical observatories, and the concordance steadies the hand. From a glow, only a few parts in 100,000 uneven, he now weighs the invisible and times the building of structure. The oldest light also remembers the dawn of the first stars. The reionization of hydrogen leaves a large-scale polarization imprint that reports when new ultraviolet photons begin to carve holes in the neutral fog. Early estimates place that dawn surprisingly soon, then later analyses push it forward in time, and with each refinement, galaxy formation models adjust their recipes for how gas cools and fragments. Every revision narrows a corridor through which any theory of the beginning must pass, because the first light and the first stars must fit a single timeline. The map does not only constrain what is present, it bounds what could have been. If the early universe hosted exotic defects such as strings of trapped field energy, or sudden phase transitions that broke perfect symmetry, their gravitational pull would have drawn straight scars or hot and cold wakes into the background. The strongest versions of such relics are ruled out by the smoothness of the data, yet delicate variants still hide within the margins, and searches continue for specific patterns that would betray them. The absence of obvious scars is itself a sign. Whatever triggers the beginning leaves a surface so even that only the smallest wrinkles survive. He steps back from the sea of pixels and thinks about how improbable it all looks. Noise becomes structure. Randomness sets the stage for galaxies that later kindle stars and planets. The map is both a ledger and a lure. It tells him the universe is flat within present sensitivity that matter and energy budget, to specific fractions that the spectrum of primordial ripples is almost scale-free. It also places a quiet finger on a few stubborn features that do not slide neatly into the template: the broad deficit of large-scale power, the preferred orientation of the largest modes, and the cold patch remain within statistical allowances yet refuse to vanish under repeated scrutiny. They sit like knots in a smooth plank, reminders that the wood once grew as a living tree. He does not name a cause. He does not need to. The oldest light has already set the terms. Any story about a spark that precedes this glow must deliver a horizon that explains the uniformity, a nearly flat geometry, a spectrum that tilts just enough a timetable that permits the first stars to reionize the medium, and a graceful explanation for why a universe so broad behaves as if it were once in close conversation with itself. He closes the maps for now, but the afterimage remains a sky-sized fossil that shifts a simple question into a grander one. If there was nothing, why does the first light look as if something had already arranged the stage? He turns to the idea that the universe begins its visible life with a brief and astonishing sprint, a period when space itself expands faster than any light could cross it, not by breaking the rule that limits motion through space, but by changing the scale of space in which motion is measured. This episode, called Inflation in the language of cosmology, smooths unevenness, flattens curvature, and stretches microscopic fluctuations into the seeds of future structure. It answers the riddle of why the oldest light looks the same in regions that should never have been in contact by asserting that those regions were once close neighbours before the expansion pulled them apart beyond each other's horizons. It explains why space appears flat on the larger scales, because exponential growth pushes any initial curvature towards zero, the way the surface of a balloon looks flatter when seen in a small patch. He stands in front of the ledger of observations and sees that inflation fits many entries with elegant ease, the near uniformity of the cosmic microwave background, the nearly scale-free pattern of tiny temperature variations, the lack of troublesome relics that would have marred the early sky. Yet he does not mistake an explanation for a mechanism. To name inflation is not to identify what drives it. The mathematics invites a field whose energy remains almost constant for a brief time, a field that rolls slowly down a gentle slope of potential energy, and in doing so acts like a temporary vacuum energy that fills space uniformly and pushes it to expand at an accelerating pace. When the field finishes its slow roll and falls into a true minimum, its stored energy decays into the particles and radiation that will later build stars and galaxies of violent reheating that turns a nearly empty expanse into a hot, dense state that resembles the beginning described by older Big Bang pictures. The story is simple to narrate and hard to realize with convincing detail. He asks how long this sprint must last, and the answer, written in the language of exponential growth, requires roughly 60 foldings of the scale factor to iron out old wrinkles and stretch a small patch into our entire observable universe. He asks how gently the energy must change, and data from the Planck mission and ground-based polarization experiments narrow the possibilities to potentials that are flatter than once imagined, because a steep slope would generate gravitational waves too strong to hide from the delicate curl patterns sought in the background's polarization. The current limits reported in terms of the ratio between the amplitude of primordial gravitational waves and the amplitude of the density ripples push that ratio to be less than a small fraction, and each improvement prunes whole families of once fashionable models. He watches this pruning with a curious calm. The absence of a detected swirl does not deny the inflationary idea, but it urges a quieter inflation driven by a field that barely moves until it must. The same maps tell him that the density ripples are nearly Gaussian, which is to say their statistics follow a bell curve that betrays little sign of wild interactions in the process that stretched them. That quietness again trims the landscape of theories and suggests that if any exotic interactions were present, they were modest. Even so, the data leave room for whispers a slight tilt in the spectrum that favours larger scales by a small margin, and hints still contested of hemispherical differences and alignments that sit at the edge of chance. He wonders whether these features are flukes, the inevitable oddities that arise when one draws a single universe from a probabilistic process, or if they are footprints of a more structured beginning. The engine itself remains enigmatic. Some proposals borrow fields from particle physics, and their symmetry breaking patterns. Others invent a new inflaton, whose sole task is to drive this expansion, and still others attempt to replace the field with modifications to gravity at very high energies. Each path carries questions. A field tied to known particles must thread a narrow needle to match laboratory constraints while performing cosmic work. A new field must not appear gratuitous yet. In practice, it often does. Altered gravity must reduce to the familiar form when energies fall, and doing so without leaving unwanted traces is delicate. He considers the graceful exit problem the need to end inflation everywhere, and to do so in a way that fills space with hot radiation rather than pockets of cold emptiness. Quantum tunneling from a false vacuum could start the process with bubbles of true vacuum that expand at near light speed, but if bubbles collide too rarely, they leave an empty cold background between them, and if they collide too often, they mar the residual sky with scars. The slow roll picture softens this by turning the end into a continuous decay, yet it still must couple to ordinary particles to make the hot plasma, and those couplings can reintroduce conflicts with other constraints. He notes that at the highest energies where this all unfolds, the distinction between quantum fields and the geometry of space-time blurs, and some argue that a complete theory of quantum gravity is required to make these speculations truly safe. Others point out that inflationary predictions for observable quantities depend mostly on a narrow band of energies far below the Planck scale, where such a full theory might dominate, and that careful, effective descriptions suffice. The debate itself becomes a sign of the limits of present knowledge. He walks further into the implications. If the field's slow roll is gentle enough, and its quantum fluctuations are large enough, then inflation may not end everywhere at once. In some patches the field fluctuates back up the potential, even as it rolls downward on average, prolonging the accelerated expansion in those regions. The result is eternal inflation, a future in which new cosmic regions continue to bud off and thermalize while others keep inflating. Each pocket becomes a universe with its own history, and if the physics permits multiple low-energy outcomes, then different pockets carry different constants, particle masses or symmetry patterns. This picture produces a multiverse not as a flourish, but as the natural behavior of a field subject to quantum noise on a potential energy landscape. He does not lean on this as an answer because it replaces one mystery with many, but he keeps it in mind when he stares at the peculiar fact that the constants of this universe seem tuned to allow structure and chemistry to flourish. Eternal inflation also leaves possible signatures collisions with neighbouring bubbles, might imprint disks of special temperature or polarization patterns on the cosmic background, and careful searches have looked for them. None stand beyond doubt. He turns to alternatives that deny the sprint altogether. There are contracting scenarios where a slowly contracting phase smooths and flattens the universe before a bounce into expansion, and there are cyclic pictures in which phases repeat, with each turnaround washing away accumulated irregularities. These models avoid an inflaton but must transmit their smoothing without leaving marks that today's instruments would have seen, and they must pass through the bounce without generating uncontrolled entropy or unwanted relics. Their own predictions for the spectrum of initial fluctuations can mimic those of inflation in broad strokes, which keeps the contest open. He reflects that the present evidence favours an early epoch that behaves like inflation, yet the driving physics remains hidden behind a veil. In that veil he places the spark that the title demands. Perhaps the inflating patch arises from a quantum fluctuation in a pre-existing vacuum, a low-probability event that becomes overwhelmingly consequential once expansion magnifies it. Perhaps the inflaton is not a single field, but an emergent behavior of many fields entangled in a hot, high-energy stew. Perhaps what looks like a field is the average effect of a changing geometry, a stitch that appears smooth only when seen from far away. Every possibility must address the same book of facts near uniformity, with tiny ripples near flatness, a specific tilt in the spectrum, a lack of strong non-Gaussian fingerprints, and a limit on primordial gravitational waves that tightens as instruments improve. He senses the paradox that clarity brings him back to wonder. The smoother inflation makes the universe, the more it hides its own cause. A process that wipes away memory also wipes away the clues that would identify it. He accepts this not as defeat, but as the shape of a deeper question. The whisper of inflation is a whisper precisely because it is a smoothing wind. The task is to listen for the eddies that remain, and to decide whether they are debris of chance or the residue of a more intricate beginning. He follows the birth of structure back to the smallest tremors, to quantum fluctuations that live in the vacuum when the universe is still a baby, and then become the scaffolding of all later forms. A quantum fluctuation is a brief borrowing of energy allowed by the uncertainty at the heart of quantum theory, a jitter that cannot be banished even in a perfect vacuum. During a period of rapid early expansion, those jitters are stretched from microscopic to cosmic scales. Each ripple is described as a mode, a wave with a particular wavelength. While the universe inflates, a mode begins well within the local horizon, which is the region where causes can affect effects. Expansion pulls the wavelength longer until it exceeds the horizon. Once outside, causal forces cannot smooth it further, and the mode becomes effectively frozen in amplitude. When the accelerated growth ends and ordinary expansion resumes, the horizon grows faster than the stretched wavelengths, and modes eventually re-enter. At re-entry, the frozen pattern reawakens as a seed for density variations. Regions that were slightly denser become the nurseries of galaxies, while regions that were slightly thinner sink into voids. This passage from quantum to classical is subtle, and he lingers over it. The fluctuations begin as quantum states with uncertainty in phase and amplitude. Interaction with the surrounding environment, even if that environment is only the collective gravitational field of many other modes, can cause decoherence, a process in which quantum superpositions lose their delicate phases, and the outcome looks classical. The result is a squeezed state where the uncertainty in one property is small, while the uncertainty in the conjugate property is large, leaving a definite pattern in the sky that can be treated as a classical field. The universe itself becomes the measuring device, and the pattern that will guide the formation of clusters and filaments is laid down not by intention, but by the silent arithmetic of expansion and decoherence. He checks the statistics of those seeds against the maps and surveys. The simple picture predicts that the fluctuations follow a nearly scale-free spectrum, meaning that the amount of variation is almost the same across a wide range of scales, with a slight tilt that gives a little more power to larger modes. It predicts nearly Gaussian statistics with deviations so small that only a vast survey could ever see the difference, and it predicts coherent phases that show up later as the regular spacing of acoustic peaks in the ancient light. The Planck mission ground-based telescopes and large galaxy surveys agree with the broad picture. The observed tilt matches a gentle departure from perfect scale freedom, and the non-Gaussian measures remain tiny. Baryon acoustic oscillations, which are fossil sound waves preserved in the distribution of galaxies, mark a preferred scale that lines up with the same physics that patterns the oldest light. He watches the way this simplicity coexists with suggestive anomalies. Some measurements hint at features in the spectrum, small wiggles or steps that could arise from temporary interruptions of the early expansion, or from a structure in the underlying potential energy landscape. Others look for isocurvature modes, which would represent differences in the composition of the early soup, rather than pure curvature ripples. Such modes could be seeded if more than one field is active during the earliest times, as in curvaton scenarios, where a second field later converts its fluctuations into density seeds. Thus far, the evidence for such additions is weak, but the doors are not fully closed. The absence of big deviations does not prove a single field. It merely prefers economies of behavior. He lifts his gaze from the statistics and imagines the cosmic web that grows from those seeds. In a universe dominated by cold, dark matter and a smooth dark energy that accelerates the late-time expansion, small fluctuations grow first. Gravity gathers dark matter into halos, and baryons fall into the potential wells cool by emitting radiation and begin the cycle of star formation. Through mergers and accretion, halos build a hierarchy that links dwarf galaxies to giants, while sheets and filaments interlace into a web that girds the sky. The voids between filaments expand, becoming cleaner of matter with time. He sees how the initial power spectrum determines the abundance of halos of different masses, how it sets the characteristic scale of voids, and how it controls the timing of the first stars that produced the ultraviolet light needed to reionize the hydrogen fog. In this way, the whisper of quantum fluctuations dictates the calendar of cosmic dawn. He uses new tools to test the seeds at different scales. The Lyman alpha forest, which is the pattern of absorption, features in the spectra of distant quasars, probes the fine-grained structure of gas, and thus the small-scale power that the initial spectrum provides. Weak gravitational lensing measured as systematic distortions in the shapes of background galaxies maps the total mass directly and checks the predicted growth rate. Forthcoming surveys by the European Space Agency mission named Euclid and by the Vera C. Rubin Observatory will stretch these tests across more sky and deeper time. Radio work that hunts the faint spin-flip signal of neutral hydrogen at long wavelengths adds a fresh handle, promising a three-dimensional movie of structure growth from the Dark Ages through the era of the first galaxies. These measurements can expose any small departures from the simplest seed spectrum, and so pry open the earliest minutes of history. He cannot resist a more speculative branch that grows from the same root. What if the initial power increases sharply on some particular small scale? Then when such modes re-enter the horizon, their overdensities could collapse into black holes before pressure and turbulence disperse them. These primordial black holes would be born long before stars, and in some ranges of mass they could contribute to the dark matter or seed the supermassive black holes that sit at the centers of galaxies. Microlensing searches that look for the temporary brightening of stars as compact masses cross their lines of sight, as well as dynamical limits, and radiation constraints rule out many possibilities but not all. Gravitational wave observatories add a new test, since mergers of ancient black holes would produce a pattern of events and a background hum of waves. If such evidence appeared, it would not only solve a dark riddle, but also point straight back to special features in the quantum seeds. He returns to the challenge of explanation. The regularity of the data can look like a fingerprint of chance, the inevitable outcome of a vast ensemble of possibilities, and yet order appears at every turn. Phases are aligned in just the right way to produce the acoustic peaks. The statistics are almost perfectly Gaussian, as if every complicated interaction knew to hold its breath. The tilt is small, and in the direction most expected for a slow change in the engine that stretches space. Perturbations in curvature dominate over perturbations in composition, a fact that prefers simple beginnings. He wonders whether this elegance is telling him that the underlying cause is almost trivial, or whether it is telling him that the underlying cause is very rich, but projects only a simple shadow on the scales he can see. He keeps a short list of temptations. A sudden feature in the seed spectrum could be a relic of a temporary pause or turn in the early expansion. A small admixture of isocurvature could betray more than one field at play. A subtle departure from Gaussian forms could hint at interactions that are too weak to leave other marks. Each of these would be another thread leading back to the first moments, a thread to be followed with colder detectors, wider surveys and finer maps. For now, the forest of galaxies, clusters and filaments stands as a monument to quantum whispers. The path from vacuum jitter to the arrangement of everything is not magic. It is a chain of cause that begins with fluctuations, fixes them in place by stretching them beyond causal contact, allows them to re-enter as initial conditions, and then lets gravity and cooling do the rest. He sees that the story is complete enough to be convincing and incomplete enough to be compelling. The seeds are random, yet their harvest looks organized. The numbers look natural, yet their harmony feels deliberate. The map of the oldest light, the distribution of galaxies, the weak lensing fields, and the absorption forest all sing one melody that began as a tremor in nothing. He allows that this may be what the question demands. If there was nothing, then perhaps the first thing to appear was a pattern. And perhaps the pattern was only the most delicate structure that a vacuum can sustain, stretched to a scale where it can be seen. He steps into the hotter, earlier frame where simplicity looks like perfection. At the highest energies that the young universe can carry, the familiar catalogue of forces may be different faces of a single order. He pictures a symmetry so broad that it treats particles that later behave very differently as indistinguishable members of one family. Symmetry here means that a transformation leaves the underlying rules unchanged, and the larger the symmetry, the fewer independent rules remain. In the earliest moments, when temperature erases distinctions, the laws may rest in such a wide symmetry that no mass separates one species from another, no range limits one force more than another, and no direction is privileged. Cooling then acts like a sculptor's chisel, and each drop in temperature selects one contour from many possibilities, hiding part of the original symmetry and releasing new behavior. A tidy order fractures with puzzling precision. He begins with the electroweak union. Today, electricity and magnetism form a single force that stretches across space with infinite range, while the weak nuclear force looks separate and short-ranged, responsible for certain decays and for processes that helped set the balance of light elements in the first minutes. In a hotter past, an electroweak symmetry binds them into one framework with massless carriers and equal footing. A field called the Higgs field takes on a non-zero value throughout space when the temperature falls below a critical scale, and that value hides part of the symmetry. The hiding is not a deletion, but a change in how the vacuum chooses to sit like a ball, rolling from the peak of a hill into a valley and staying there. Particles that interact with the Higgs field acquire inertia as they move through this new background. They gain mass not as a substance added, but as a relationship to a field that now permeates space. Force carriers that couple to the Higgs field become heavy and thus short-ranged, while the photon remains massless and roams freely. The same cooling that splits one elegant union births the clutter that later makes chemistry rich. He widens the frame to the possibility that even this electroweak union once sat inside a grander symmetry that also included the strong nuclear force which binds quarks inside protons and neutrons and glues nuclei together. In such a grand arrangement, quarks and leptons that today seem unlike are organized side by side in larger multiplets, as if the categories that later feel natural were late inventions. The strengths of forces change with energy, and when he tracks those changes upward, they appear to draw toward one another, as if hinting at a meeting point at energies far beyond any machine now on Earth. Various versions of this grand order make predictions that reach into experiment. Some predict that a proton is not absolutely stable, but may very rarely decay into lighter particles with a lifetime so long that it dwarfs the age of the universe. Huge tanks of ultra-pure water and liquid scintillator sit in underground caverns to wait for the telltale light of such an event, and the absence of a signal so far pushes the scale of any such unification higher and prunes many models. Yet the absence does not kill the idea. It forces tighter tuning and raises the intrigue that unity hides farther back behind the curtain than expected. Symmetry breaking at very high energy also suggest cosmic fossils. When a continuous symmetry breaks, the vacuum can choose different orientations in regions that were once out of causal contact, and the boundaries between those regions can host relics called topological defects. Cosmic strings would be line-like concentrations of energy stretched across space-domain walls, would be sheet-like boundaries separating distinct vacua, and monopoles would be point-like objects that behave as isolated magnetic charges. He reads the sky as a record of which defects were allowed to remain. There are no domain walls of cosmic scale, which reassures him, because a network of such sheets would over-dominate the universe. There is no crowds of monopoles either, although some theories suggest they should have been created in abundance during grand breaking. Here an earlier chapter returns as a remedy. If a period of rapid expansion occurs after such relics are born, it can stretch space so dramatically that their density in our observable patch becomes vanishingly small. That same expansion smooths the horizon puzzle of the oldest light, and so a single process may both iron the map and clean the debris. The elegance of this double service does not prove it true, but it persuades him that the pieces fit in a way that is not accidental. He follows another consequence of unity followed by fracture, the origin of the slight excess of matter over antimatter. If the early universe began with equal parts of each, almost everything should have annihilated into light, leaving a thin residue. Instead, there remains a small excess of matter that builds every star, planet, and person. For that excess to arise from symmetric beginnings, 3 conditions must be met. Interactions must exist that do not conserve baryon number, which is the count of heavy matter minus heavy antimatter. The symmetries of charge and mirror reversal must be violated so that processes and their mirror reflections do not run at equal rates, and the system must be out of thermal equilibrium so that inverse reactions cannot erase any created imbalance. Grand unification naturally provides reactions that let baryon number change. Known interactions in the weak sector do violate the combined charge and mirror symmetries in measured ways, though perhaps not strongly enough by themselves. Phase transitions during the cooling of the early universe supply departures from equilibrium, especially if they are first-order transitions in which bubbles of a new phase nucleate and expand through an older one. He imagines a hot sea in which tiny bubbles of a lower energy phase appear, grow, and collide with the boundaries acting as temporary factories where the needed asymmetry is catalyzed. Whether this happened depends on the detailed shape of the Higgs field potential and any fields coupled to it. Calculations and collider measurements suggest that in the simplest setup, the electroweak transition may have been a gentle crossover rather than a dramatic bubbling, which would mute this route to producing the asymmetry. That in turn motivates extensions that alter the thermal shape of the potential, adding new fields or interactions that could restore a stronger transition without spoiling what has already been measured. Each such possibility is a door cracked open between cosmic history and terrestrial experiment. He returns to the Higgs field as more than a giver of mass. its potential energy curve may admit multiple valleys separated by hills. If the present vacuum is only metastable, quantum tunneling could one day carry the field to a deeper valley, rewriting the pattern of masses and couplings. The measured masses of the Higgs boson and the top quark place our valley near a boundary between absolute stability and long-lived meta-stability. The timescale for any transition is so immense that for all practical purposes the vacuum is safe. Yet the proximity to this boundary teases at a principle not yet stated, as if the parameters were balanced on a ridge for a reason that has not been named. Another symmetry hides within the strong force itself. The equations allow a term that would make the strong interaction violate the paired symmetries of charge and mirror reversal, a term that would give the neutron an electric dipole moment. Decades of careful measurements have set extremely small upper limits on that moment, which implies that the offending term must be fantastically tiny, or must be driven towards zero by a mechanism. A proposed remedy introduces a field that relaxes this term dynamically to nearly nothing. The associated particle would be a very light pseudoscalar that interacts feebly with ordinary matter. If it exists, it could be produced in the early universe and survive as a cold, nearly invisible component that might supply some or all of the dark matter. Telescopes and laboratory searches explore the narrow windows where such a particle might reveal itself as a faint conversion of light in a magnetic field or as a tiny oscillation in resonant circuits. Here again, a solution to a puzzle of symmetry doubles as a candidate for an unseen cosmic inventory. He watches how this sequence of breakings achieves contradictory goals. It begins with an austere order that favors unity and erases distinctions, cooling fractures that order just enough to allow variety masses appear. Ranges change composite objects form and nuclei and atoms become possible. The timing must be precise. Break too soon and some transitions cannot power the departures from equilibrium needed to forge the matter excess. Break too late and relic species remain too abundant, upsetting the counts inferred from the oldest light and from the light elements. Break in the wrong pattern, and topological defects choke the cosmos. What remains in the data is a narrow corridor of success. The universe behaves as if it moved through a sequence of thresholds that were both gentle enough to preserve uniformity and dramatic enough to seed the asymmetry and structure that followed. He ends this step with a paradox sharpened. High symmetry looks like nothingness made law a state with few descriptors and no preferred directions. The world he sees today is a rich collection of specifics that works because that high symmetry broke in just the right ways at just the right times. The precision of those fractures does not yet arise from a principle he can point to. It arrives as a set of measured facts that ask to be woven into a cause. He holds both pictures at once, an early, almost featureless rule that would fit on a short line and a later garden of phenomena that needs a book. The fracture from one to the other looks less like damage and more like instruction. Something in the way the universe cooled carried a script that knew when to loosen its grip. He follows the arrow that seems to run through every process, the steady tendency for order, to give way to disorder, for heat to spread, for mixed states to replace separations. And he asks why time has a direction at all. The rules of fundamental interactions, as written in the language of fields and forces, look nearly reversible when viewed at the smallest scales. If a film of microscopic collisions is played backward, the equations carry it just as faithfully as they do forward. Yet in kitchens, engines, stars, and galaxies, a preferred direction appears. He calls that direction the arrow of time, and its guide is entropy, a measure of how many microscopic arrangements correspond to the same macroscopic appearance. When the number of compatible microstates is larger, entropy is higher. The second law of thermodynamics then states that In an isolated system, entropy tends to increase not because any single path is forbidden, but because the paths that raise entropy are overwhelmingly more numerous than those that lower it. He looks for the origin of this bias, and finds that it cannot arise from the reversible equations alone. It must be laid down in the boundary conditions in the special character of the state from which the universe begins. The early universe is hot and dense, filled with radiation, and a smooth plasma that leaves a nearly uniform glow as a fossil. By some measures, the thermal entropy of this fireball is high even then. But gravity changes the accounting. A uniform distribution of mass has low gravitational entropy because gravity prefers clumping that leads to collapsed objects and eventually to black holes, which carry extraordinary entropy proportional to the area of their horizons. The smoothness of the early state, the very evenness celebrated in the map of ancient light, is therefore a sign of enormous gravitational order. As structure forms matter, falls into wells, stars ignite, galaxies assemble, and black holes grow, and the total entropy skyrockets. The arrow of time emerges as the universe moves from a remarkably smooth beginning to a richly clumped present, and toward a future where black holes dominate the entropy budget. He traces this insight to a question sharpened by Ludwig Boltzmann. If an overwhelming majority of microstates correspond to high entropy, why did the universe ever start in a state of such improbably low gravitational entropy? One response is a simple statement sometimes called the past hypothesis. The universe began in a very special low entropy condition, and all observed arrows follow from that fact. The hypothesis is a boundary condition rather than a dynamical law. It tells him what to assume, but not why to assume it. He pushes further and considers the shape of space-time itself. Roger Penrose proposed that the curvature associated with tidal distortions, encoded in what geometers call the Weyl curvature, vanishes, or is constrained near the beginning, and that this condition expresses the low gravitational entropy of the initial state. Later, as matter collapses and horizons form, the Weyl curvature grows, and with it the gravitational entropy. The proposal is not yet a theory derived from deeper principles, but it is a clear way to mark the specialness of the start using the language of geometry. He watches how the cosmic expansion participates in the arrow. As space grows, it creates new room for entropy to increase. Thermal radiation cools with the expansion, but structure formation produces gravitational clumping, nuclear burning, and shocks that generate entropy. The first stars act as engines that take free energy, stored in the contrast between dense clouds and surrounding emptiness, and convert it into radiation and heavy elements. Galaxies then recycle gas through supernova explosions, and black holes heat surrounding material as it spirals inward. Each of these steps pushes entropy upward while exporting energy as light that streams into the wider universe. The arrow he sees in a cup of tea is the local face of the same global slide, powered by ancient free energy that gravity unlocked. He revisits classic paradoxes to test this story. The Loschmidt reversibility objection notes that if the microscopic laws are time-symmetric reversing, every velocity would make entropy decrease. He answers that such perfectly contrived states are fantastically rare in the space of possibilities, and that the past hypothesis forbids the kind of finely tuned initial correlations that a global reversal would require. The Poincaré recurrence argument observes that a finite isolated system will eventually return arbitrarily close to its initial state given enough time. He answers that the observable universe is not a finite gas in a box with rigid walls. It expands, creates horizons, and hosts black holes that swallow information behind one-way surfaces for phenomenally long times, so the simple recurrence picture does not apply in any practical sense. He also notes that even in a future dominated by a smooth, dark energy that accelerates expansion and yields a de Sitter-like state with its own temperature and horizon entropy, the relevant timescales are so large that any fluctuation-driven recurrence is astronomically remote. He does not ignore the sting in that last thought. In a very long-lived de Sitter, future rare thermal fluctuations could assemble observers with false memories more readily than they would regenerate a low-entropy cosmos like the one that began our history. These so-called freak observers raise an uncomfortable challenge to any account that leans solely on chance in a timeless background. He takes the challenge as a sign that a deeper account is still missing, one that ties the low entropy beginning to dynamics rather than to blind selection in an eternal bath. He connects the arrow to the chemistry of life without granting life any special status. Stars create heavy elements, planets condense, and gradients of energy drive complex cycles that harvest free energy and dump entropy into their surroundings. The very possibility of sustained complexity is tied to the availability of temperature and density contrasts, which in turn depend on the universe not being born in maximal entropy. If the early cosmos had begun in a fully clumped state, black holes would have ruled immediately, and the sky would have been cold, dark, and uneventful. If it had begun in perfect thermal equilibrium with no gradients at all, nothing would have happened. The observed history sits between these dead ends because the initial condition is exquisitely even in distribution, but poised to unlock free energy through gravity as expansion proceeds. He contemplates whether the arrow can be derived from a more fundamental principle. Perhaps the beginning is an attractor of a law that selects smooth, low-while curvature geometries, making what looks like a miracle into a rule. Perhaps the spark that initiates expansion also erases previous clutter, as in models where a bounce from a prior phase resets gravitational degrees of freedom to a quiet state. Perhaps space-time emerges from quantum entanglement in a way that enforces special initial correlations, so that low gravitational entropy is not a coincidence, but a consequence of how geometry is woven from information. He does not claim any of these as settled. He holds them as sketches that respect the data and the logic of the arrow. He also notices how the early uniformity that inflation promotes would naturally lower gravitational entropy, since stretching any inhomogeneity thin makes the mass distribution smoother. Yet he recalls that inflation itself requires initial conditions, and that a simple wave of smoothing cannot explain why the pre-inflationary patch is already regular enough to start the process. The arrow therefore remains a compass that points back to an origin whose specialness is not yet fully explained. He looks ahead and sees the arrow continuing. Black holes grow by swallowing gas and stars and by merging with each other, and their horizons carry the largest known entropy per unit mass. Over unimaginable times, ordinary matter decays, or as ejected galaxies fade and the sky empties as accelerated expansion drives distant regions beyond contact. Black holes slowly evaporate by emitting quantum radiation, returning their mass to diffuse light, and leaving behind a thin bath of quanta at very low temperature. The entropy gained in these processes does not reverse, it spreads. The universe drifts toward a heat death in which free energy that can perform organized work is scarce. The arrow does not point toward a goal, it points toward a leveling. He ends the step with a sharpened question. The arrow of time seems to be the shadow cast by an extraordinarily low entropy beginning. The data tell him the beginning is smooth and nearly uniform, which is exactly what low gravitational entropy requires. The logic tells him that such a beginning is special. What is not yet told is why the universe chose it. Until that part of the story is written, The arrow remains both an explanation for everything that unfolds and a reminder that the first page is missing. He turns to the imbalance that gives matter a future. The visible universe carries a slight excess of particles over antiparticles, a few parts in 10 billion enough that after nearly all pairs annihilate into light, a thin remainder survives and gathers into stars, planets, and the long chemistry of life. This excess is not an afterthought, it is the difference between a sky of radiation and a cosmos with storylines. He sets down the 3 signposts that any successful explanation must pass. There must be processes that change the total count of baryons so that matter can be created from near balance. There must be violations of combined charge reversal and mirror reversal so that the forward path is not neutralized by its mirror twin. There must be departures from thermal equilibrium so that inverse reactions cannot unwind any created excess. These rules distilled by theory do not tell him which road was taken, but they mark every road that could work. He searches the early universe for factories that meet these conditions. The weak interaction already violates the symmetries of charge and mirror reversal in measured ways woven into the angles and phases of the Kabibo-Kobayashi-Maskawa framework that mixes quarks. Particle colliders and dedicated experiments have mapped these violations with exquisite care, yet when he translates those numbers into the expected matter excess, the result comes out far too small by many orders of magnitude. The known mechanism whispers when the cosmos needed a shout. He considers whether the electroweak epoch could have supplied the needed non-equilibrium. If the cooling universe once crossed a sharp threshold, where bubbles of a new phase nucleated and expanded, the walls of those bubbles could have acted as moving laboratories where the required asymmetry is catalyzed. But the most economical picture of the Higgs field suggests the transition was a gentle crossover, too soft to drive a strong asymmetry. That pushes him toward extensions of the field content, or the interactions that can sharpen the transition, without spoiling what colliders have already seen, a delicate dance in which cosmology and experiment clasp hands. A different doorway opens when he remembers that the total count of baryons is not the only tally that high-temperature physics can alter. In the hot plasma above the electroweak scale, rare non-perturbative processes called sphaleron transitions shuffle baryon and lepton numbers together while preserving their difference. If an earlier stage produced a surplus of leptons, these electroweak reactions could partially convert that surplus into baryons before the universe cooled past the relevant threshold. This is the path called leptogenesis, and it shifts the mystery from baryons to neutrinos. Neutrinos carry 2 striking clues. They oscillate from one flavor to another as they travel, which means they have mass and mix, and that mixing may contain a phase that violates charge and parity in the lepton sector. They may also be their own antiparticles, which is to say that a neutrino and an antineutrino could be the same entity with opposite spin, a property called Majorana nature. If neutrinos are Majorana particles, then the simplest way to make their masses small is to introduce very heavy right-handed partners that hardly interact with anything familiar. When these heavy neutrinos exist in the early universe, they can decay out of equilibrium, and with a built-in preference for matter over antimatter, producing a lepton asymmetry that sphalerons later convert into a baryon asymmetry of the observed size. The attractiveness of this picture is doubled by parsimony. The same architecture that explains tiny neutrino masses offers a factory for the matter excess. He watches the observatories that could turn this sketch into a measured story. The deep underground neutrino experiment will drive intense beams through the Earth to a far detector to hunt for large violations of charge and parity in neutrino oscillations. The Hyper-Kamiokande detector will amplify the sensitivity of water Cherenkov methods to the same effect. the Jiangmen Underground Neutrino Observatory will weigh mixing angles and mass ordering with fine resolution. Neutrinoless, double beta decay experiments such as Kamland Zengerda and Quora listen for the silent emission of 2 electrons without accompanying neutrinos a smoking gun for the Majorana character. A confirmed signal would make the early lepton factory far more believable. He balances this pathway against alternatives that couch the needed asymmetry in the quark sector or in more exotic realms. There are models with new scalar fields that couple to quarks and open fresh sources of charge and parity violation at high temperature. There are scenarios where the Higgs sector itself is extended, turning the electroweak change into a dramatic first-order transition with bubble walls that bias particle transport. There are models that borrow ingredients from grand unified frameworks, where decays of heavy bosons present only at tremendous energies, violate the baryon count directly, and play out long before the electroweak epoch. Each path leaves fingerprints, and he keeps track of the ways those prints could be found. Measurements of electric dipole moments in the neutron in atoms and in molecules squeeze the room for new sources of charge and parity violation at low energy. The Large Hadron Collider Beauty Experiment and its kin probe, rare decays, and mixing in the quark sector, tightening the leash on any undiscovered phases. The absence of a signal is information to guiding theorists toward corners of parameter space that remain open and toward mechanisms that hide their asymmetry making at scales just beyond present reach. He consults the oldest witnesses because the light element abundances and the cosmic microwave background turn the matter excess into numbers with real weight. The ratio of baryons to photons measured with the precision of a few percent agrees across the fossil patterns in the background glow and the relic nuclei forged in the first minutes. Any proposed factory must deliver this ratio and must not pour additional energy into the plasma in a way that ruins the fit to the observed spectrum of ancient light. This single constraint read off a sky map has the quiet authority of a ledger. He allows himself a moment of speculation at the threshold, where initial conditions and effective laws meet. The imbalance could be a consequence of a deeper asymmetry in the fabric of quantum gravity, a built-in handedness that only appears as charge and parity violation in the low-energy world. It could be an emergent phenomenon tied to the instability of a vacuum poised near a transition in which tiny random choices are amplified into a global preference as bubble walls collide. It could be a statistical selection effect in a larger landscape of regions with different phases and constants, in which only those patches with a small but non-zero excess can form long-lived complexity and thus be noticed. He does not pick among these ideas, but he does sharpen the demand that any of them must meet. They must explain why the excess is small, yet not zero robust, yet sensitive enough to be tuned by parameters that are or soon will be measured. He notes a symmetry in the narrative that mirrors the mathematical ones already invoked. The universe begins with an almost perfect balance that would lead to nothing but light, yet small violations of balance at the right moments create the possibility of everything else. The same principle repeats at many scales. A slight tilt in the spectrum of initial fluctuations, a slight excess of matter over antimatter, a slight deviation from perfect symmetry in the Higgs field, and a slight preference embedded in particle mixing angles. Each small asymmetry cascades into a grand consequence. Without the excess of a few parts in 10 billion, even the questioner would vanish into the glare. With it, galaxies thicken, stars ignite, and time becomes a carrier of memory. He returns to the instruments that listen for the missing evidence and finds comfort in their variety. Underground caverns filled with silent tanks, kilometre-long baselines, that fling neutrinos through rock cryogenic crystals tuned to hear a whisper of forbidden decay, precision traps that measure the shape of an electric field around a neutron to absurd accuracy. Each of these is a net cast into the dark water of the first seconds. The nets have begun to tug. Hints of large charge and parity violation in neutrino oscillations flicker in early datasets. Limits on electric dipole moments fall by orders of magnitude, pruning entire classes of models. Collider analyses constrain the shapes of extended Higgs potentials. None of this yet writes the origin with ink that will not fade, but the lines on the page are growing darker. He ends this step with a thought that binds physics to wonder. The universe that looks so balanced at the broadest scale carries within it a carefully placed imbalance that makes discourse possible. It is as if the first script contains a margin note in a different hand, small enough to be overlooked, large enough to change the plot. The search for that hand is not a hunt for purpose, but a hunt for process, and it leads him back toward the spark with a clearer set of demands. Whatever ignited the beginning did not only make space expand and fluctuations grow, it also taught matter to win by a sliver, and that sliver is the opening through which the rest of history walks. He listens for a choir that almost no instrument can hear, a sea of relic neutrinos that streams through every cubic centimetre of space, with the patience of the oldest ash. These neutrinos decouple from the primordial plasma when the universe is barely a second old, at a temperature of a few megaelectronvolts, when collisions that once kept them in step with electrons and photons become too rare to matter. From that moment forward, they free-stream cooling with the expansion and slipping just out of thermal contact, so that when electrons and positrons later annihilate and heat the photons, the neutrinos miss most of the banquet. The result is a background of ghostly quanta colder than the oldest light by a fixed factor, with a present temperature close to 2 Kelvin. Their number density is large by human standards, roughly a few hundred per cubic centimetre. When all flavours and anti-flavours are counted, and they move almost unhindered through planets, stars and galaxies. He cannot catch them with mirrors or lenses, but he can hear their effect in the patterns of the sky, and in the ledger of the first nuclei. The relic neutrino background is silent, yet not mute. It changes how the universe expands during its first few minutes and first few 100,000 years, and those changes leave fingerprints that the elements and the oldest light can record. The count of effective light species, a single number that tallies how much radiation-like stuff is present beyond the photon's shapes. The expansion rate during the era when protons and neutrons lock into helium and trace isotopes of hydrogen and lithium. If the radiation bath is thicker than expected, the expansion is faster, the window for nuclear reactions is shorter, and the final fractions shift. Astronomers weigh these fractions by watching absorption lines in ancient gas clouds and by modelling stellar atmospheres, and they compare the result to the values predicted when 3 light neutrino families carry the background. The match is persuasive, with room for a small extra note that could be an additional light species or a mild departure from perfect equilibrium. The same radiation census echoes later in the acoustic peaks of the cosmic microwave background. Relic neutrinos travel close to the speed of light when they are young, and so free stream ahead of the photon baryon fluid, adding a phase shift to the sound waves and a change to the damping tail where subtle diffusion blurs small features. Precision maps from space and from quiet deserts pick up those delicate adjustments, and when he combines them with the nuclear abundances, the tally points again toward 3 active neutrinos and a background temperature near 2 Kelvin. He takes comfort in the way 2 eras that never meet still agree on the same count. He turns from counting to weighing. Neutrinos are not massless. Their flavor oscillations prove that at least two species possess mass, and the sum of the masses those small matters for how structures grow. While the universe is hot, neutrinos behave like radiation and stream freely, but as it cools, they slow and begin to behave like light matter. Because they move swiftly for so long, they do not cluster on small scales. They wash out the formation of very small halos and slightly damp the contrast of the cosmic web, leaving an imprint that careful surveys can trace. Galaxy maps, weak lensing measurements, and the fine structure of the oldest light build a joint constraint that pushes the allowed total mass well below 1 electron volt. He watches the bound tighten year by year as larger surveys and cleaner analyses lower the noise. It is a strange experience to weigh a background that cannot be seen. The weight shows itself as an absence of fine grain, the gentlest smoothing of structure, and yet it is enough to tell him that neutrinos are light, but not weightless, influential, but not dominant. He threads these anchors to a technical dream, the direct detection of the cosmic neutrino background not by its influence, but by capturing its particles one by one. A proposed method uses a beta-decaying nucleus, most often tritium, whose electrons have a maximum energy that sets a sharp spectral edge. A relic neutrino captured by such a nucleus would trigger an electron with energy ever so slightly above that edge. An experiment named for a navigator who first mapped the sea in lines and arcs has become a symbol of this dream. It imagines a carpet of tritium thin as frost, and detectors keen enough to separate an excess that rises only a handful of events above a mountain of ordinary decays. The requirement is severe, extraordinary energy resolution, vanishing background and control of every systematic that could mimic a tiny spectral shoulder. He regards the difficulty without discouragement. The first maps of the oldest light were once fantasies too. The cosmic neutrino background will likely be heard first in indirect ways with still greater confidence, and perhaps later it will be touched. He lets speculation enter with the same discipline that has guided every earlier step. If the effective count of light species were measured to be larger than 3 by a convincing margin, it would open a door to dark radiation, a new form of nearly luminal quanta that carry energy but only feebly interact with known matter. Candidates range from sterile neutrinos which would not couple to the weak force at all, to goldstone bosons of broken symmetries in a hidden sector, to light remnants of theories that attempt to unite forces at high energy. If the count were smaller than 3 in a robust way, it could signal non-standard neutrino interactions that keep them warmer or cooler than expected, or a reheating history that departs from the simple picture of electrons and positrons, handing their heat only to photons. Each deviation would be a new verse in the early thermodynamic story. He also keeps watch for evidence that relic neutrinos interacted among themselves in the early plasma through forces beyond the weak one, because such self-interactions would alter their free streaming and reshape the acoustic pattern in distinct ways. The absence of such signs so far keeps the standard script intact, but the constraints remain elastic enough to invite surprise. He then imagines the way relic neutrinos thread through later history. As galaxies condense, neutrinos cannot be confined by shallow gravitational wells, but the deepest clusters and the halos around giant galaxies can trap a small fraction, increasing the local density above the cosmic average. This clustering is mild but not negligible, and it subtly modifies the pattern in ways that observers can one day measure. By cross-correlating maps of galaxy distributions, gravitational lensing and the background light. The scale dependence of that imprint is a ruler that reads the sum of the masses regardless of how those masses split among the flavors. The universe holds a balance that can be read with both eyes. One eye watching the past in nuclear and microwave fossils, the other eye watching the present in the geometry of maps. He considers the philosophical weight of a nearly undetectable sea. If there was nothing, then before light could speak, there were already particles that had left the conversation walking away from equilibrium and preserving a record of conditions at an age too young for any other witness. They are like scribes who left the scene before the story became noisy. Their temperature carries the ratio of how heat was shared in a violent moment. Their density carries the count of species that were present, and their masses carry a whisper of physics that does not quite fit within the neat box of the original standard model of particle physics. He sees how this faint chorus, by refusing to stop at easy thresholds, deepens the mystery rather than closing it. The background tells him that the earliest plasma was simple and hot, that the ledger of radiation and matter obeyed a narrow recipe, and that any deviation must be small. Yet the same chorus implies incompleteness. Neutrinos have mass, which demands a mechanism beyond the original script. They're mixing hints at phases that could have seeded an asymmetry between matter and antimatter through the channel of leptons. Their silence about direct interactions at late times pushes any new forces into a dark corner. Every conclusion he can draw from their existence and their influence points to both economy and remainder a minimal extension that still asks for origin. He ends the step by returning to the conceit of a symphony. The universe begins with a chord that includes photons, neutrinos, and other quanta all playing in near unison. Photons continue as the bright melody, the one that instruments on Earth can record in maps of startling beauty. Neutrinos continue as the hum that is felt more than heard, a bass line that keeps time with expansion and structure. If instruments sharpen enough to pluck a single note from that bass, the story of the beginning will fall into a new key. If not, the structure of the symphony can still be read in the spacing of the harmonics and the pacing of the rhythm. In either case, the faint chorus remains essential. It fixes the tempo of the first minute, it nudges the shape of the first sound waves, it cools and weighs just enough to matter later. It is the quietest evidence that there was a script before light, a script that was simple, strict, and somehow forgiving enough to leave a trace the present can still decode. He listens for the oldest weather in space-time, a wind that crosses the cosmos without scattering, and leaves its mark not as light but as a change in distance itself. Gravitational waves do not need a medium. They are ripples of geometry that travel at the speed of light and pass through matter, almost as if it were not there. If a storm of such waves fills the early universe, it will never fully fade. It will redshift and thin as space expands, but it will carry the memory of violence from a time that predates any photon. He calls these ripples fossils because they would tell him about processes that could not otherwise be seen. A brief burst of near exponential expansion, dramatic phase transitions in fields that once filled all space, or the snapping of defects left by symmetry, breaking like taut strings released from tension. The first place to search for these fossils is in the oldest light, where polarization can be decomposed into a gradient-like pattern and a curl-like pattern. The gradient pattern arises easily from density waves and from scattering at the time when the plasma becomes transparent. The curl pattern is harder to make. In the simplest pictures of the early universe, only primordial gravitational waves generate a curl pattern directly at large angular scales. That makes the curl a prize. He follows teams that stare at patches of sky too clean of dust and synchrotron radiation to ruin the view, and that build telescopes at special sites on high plateaus and at the South Pole where the air is dry and steady. They add more frequency bands to separate the galaxy from the cosmos, and they learn to reconstruct and remove the lensing that twists the gradient into a false curl. The strategy is careful: subtract the foregrounds with maps of many colours, de-lens the sky using reconstructions of the intervening mass, and test for systematics with rotations and splits. Earlier excitement has taught caution when a reported excess of curl-like polarization was later traced to grains of dust aligned by galactic magnetic fields. That lesson did not dampen the search, it refined it. The limits have grown steadily tighter. The ratio of primordial gravitational wave power to density wave power is now bounded to be less than a few hundredths, and perhaps even lower, and every improvement prunes families of early universe models that predicted stronger storms. This absence is a kind of presence. It favors inflating potentials that are gentle rather than steep, and that generate smaller field excursions, and it nudges alternatives that produce comparable predictions into smaller corners of their parameter spaces. He does not confuse a limit with a silence that will last. New instruments will arrive. The Simons Observatory will map the microwave sky with many bands and wide coverage. A next-generation ground effort, a stage 4 of cosmic microwave background mapping, is planned to push the delensing frontier. A small satellite from the Japan Aerospace Exploration Agency, named Lightbird, is designed to measure the large-scale curl pattern from space with exquisite control of systematic errors. If these find a curl pattern with the right shape and scale dependence, it would be a direct view of the energy scale that drove the earliest expansion. If they do not, the space of viable models will narrow to those that moved space with a quiet hand. He then turns to the later universe where gravity itself can serve as a detector. The Laser Interferometer, Gravitational Wave Observatory, has already heard the chirps of merging black holes and neutron stars as have its partners in Europe and in Japan. Those high-frequency waves come from compact binaries in the local and intermediate universe and teach him about stellar death and dense matter. The fossils he seeks are at much lower frequencies, far below what ground-based interferometers can hear. For the very longest waves, the tools are the spinning hearts of dead stars that act like clocks. Millisecond pulses flash with remarkable regularity, and if a gravitational wave stretches or squeezes the space between Earth and a pulsar, the arrival times of the pulses shift in a telltale pattern. By timing an array of pulses spread across the sky for many years, he can detect a correlated drift that betrays a background of nanohertz waves. This technique has matured into international efforts such as the North American Nanohertz Observatory for gravitational waves, the European Pulsar Timing Array, and a global consortium that unites them. These teams now report evidence for a common low-frequency hum shared across many pulses with the angular correlations expected for a gravitational wave background. The most likely origin is a population of supermassive black hole binaries slowly enspiraling at the centers of merging galaxies. That tale is already rich. It maps how frequently galaxies coalesce, how gas and stars interact with pairs of giant black holes, and how friction and slingshot encounters harden or stall their orbits. He keeps an eye on how the amplitude and the slope of the spectrum match models of this population. Yet he also keeps a corner of the mind open to an earlier origin. If cosmic strings exist, their kinks and cusps radiate gravitational power across many decades of frequency, and a network of such strings could contribute to, or even dominate the background in some bands. If a first-order phase transition shook the young universe with bubbles that nucleated and collided, the splashing of the plasma would have sent waves across space whose peaks and troughs today would fall in tranches that pulsar timing arrays and future space-based interferometers can explore. Distinguishing these possibilities will require more than a simple amplitude. It will demand the shape of the spectrum, the possible presence of non-Gaussian features, and perhaps the cross-correlation with traces of galaxies if the population of binaries is truly the driver. Another window opens at frequencies between the ground-based and the pulsar timing regimes. The Laser Interferometer Space Antenna, a joint mission of the European Space Agency and the National Aeronautics and Space Administration, will fly a triangular constellation of satellites millions of kilometers apart to measure gravitational waves in the millihertz band. It will hear compact binaries in the Milky Way, the inspirals of massive black holes at cosmic distances, and potentially any background from early phase transitions that peaks in its range. If the curl pattern in the oldest light remains dark, and if pulsar timing confirms a background dominated by supermassive black holes, then a detection by the space antenna of a separate featureful background would be a strong hint of physics in the first split seconds. He observes that each window speaks a different dialect of the same language. The cosmic microwave background curl would indicate waves stretched to scales larger than entire galaxies by early accelerated expansion. The pulsar timing background speaks of the slow dance of gargantuan binaries and perhaps of extended defects left from broken symmetries. The space antenna would attend to mid-range voices where violent transitions of fields in the early plasma could sing. Cross-checks among these bands will do more than confirm a find. They will map the spectrum of cosmic turbulence and separate the cosmic weather into its sources. Even without a detection, the search already sharpens the script. The absence of a loud curl pattern tells him that if inflation happened, it did so at an energy scale below the naive guesses from the earliest models. The absence of a large background in the millihertz range to be seen by a space antenna would constrain first-order phase transitions that may accompany symmetry breaking in extensions of the standard model of particle physics. The shape of the nanohertz hum measured by pulsar timing arrays will teach him whether black hole pairs stall at subparsec separations or are rushed along by environmental effects which in turn affect predictions for future mergers to be seen by ground and space interferometers. He takes quiet pleasure in the unity of method. All of these experiments measure distances with absurd care. Microwave polarimeters measure a pattern written on the sky in a language of gradients and curls. Laser interferometers count fractions of a wavelength along arms that stretch for kilometers on Earth, or for millions of kilometers in space. Pulsar timers compare ticks from clocks scattered across the galaxy to nanosecond precision. The same simplicity of a strain in space-time links them. Each takes a different risk of confusion from dust, from thermal drifts, from clock noise, from terrestrial tremors, from plasma in the interstellar medium, yet each has learned how to make self-checks, how to split data, how to invert and test. From these habits grows the confidence that any claimed fossil will be real or will be properly withdrawn. He ends with the thought about memory. Light remembers only what comes after the fog of last scattering. Matter remembers in the arrangement of galaxies and clusters shaped by gravity over billions of years. Gravitational waves can remember the first heartbeat. If there was nothing, the first sign that something new had happened was a change in the fabric of distance itself. Finding that change as a fossil in the background curl or in a cross-sky hum would not answer every question, but it would show that the prelude was not quiet. It would turn an inference into a sound. The silence so far has pushed models toward modesty. The next whisper, if it comes, will not only lift a curtain, but will also tell him whether the spark was a gentle wind or a thunderclap. He examines the idea that nothing is not empty, that even when all particles are gone and all fields are set to zero in the classical sense, the quantum version of emptiness still seethes with fluctuations, condensates, and latent energies that can move the universe. A quantum field cannot be perfectly still. Uncertainty enforces jitter, and that jitter gives the vacuum a baseline energy called zero-point energy. He knows this is not only a mathematical trick. Two uncharged metal plates placed very close together in a laboratory feel a tiny force that arises because the quantum vacuum allows fewer electromagnetic modes between the plates than outside them. Spectral lines in atoms shift by amounts that match calculations that include vacuum fluctuations. These are small effects in ordinary settings, yet they are precise beacons that the ground state of a field has structure. When he carries this structure into cosmology, it expands into a grand puzzle. The observed acceleration of the universe suggests a smooth energy density that permeates space and does not thin as matter disperses. When this is modelled as a constant energy of the vacuum, the fit to supernova distances to baryon acoustic oscillations and to patterns in the oldest light is impressive. The inferred density is small in human units, like a handful of protons worth of mass spread across a cubic meter in energy form, but it is cosmically decisive. A universe with such an energy in its vacuum eventually accelerates, driving distant galaxies beyond reach and washing the sky clean of structures not already bound by gravity. Yet when he tries to compute this vacuum energy by summing the zero-point contributions of known fields, the naive result overshoots the observed value by more than 100 orders of magnitude. Even if a high-energy cutoff is placed at scales where new physics should intervene, the difference remains vast. The same physics that explains tiny shifts in atoms threatens to overwhelm the cosmos with a catastrophic prediction. He calls this mismatch the cosmological constant problem, a name that is too mild for a question so sharp. One approach invokes symmetry. If there were an exact symmetry that forced boson and fermion contributions to cancel in perfect pairs, the vacuum energy could be driven toward zero. But any such symmetry must be broken at low energies to match the observed spectrum of particles, and the breaking reintroduces a residue that is still far too large unless the breaking is tuned with absurd precision. Another approach treats the problem as an issue of how gravity couples to vacuum energy, suggesting that the part of the vacuum that would curve spacetime is somehow screened or sequestered, while leaving gravity to respond normally to ordinary matter and radiation. There are proposals that modify gravity in the infrared, changing how the curvature responds to a uniform background. Each of these attempts preserves parts of the tested theory, while altering either the way fields add up in the vacuum or the way geometry reads their sum. None has yet passed from clever mechanism to accepted remedy. He then asks whether the vacuum can be more than a constant. A quantum field can carry a potential energy landscape with valleys and hills. If the field sits high on a gentle slope or near a plateau, its potential energy can act like a temporary vacuum energy that remains nearly constant across space, driving accelerated expansion. This is the essence of inflationary dynamics on a slowly rolling field, which already helped explain the uniformity and flatness of the observed sky and the origin of the seed fluctuations. The same language extends to other possible early transitions. If a field is trapped in a false vacuum, a local minimum that is not the global ground state, it can escape by quantum tunneling nucleating bubbles of the true vacuum that then expand at near the speed of light. Collisions of these bubbles and the motion of their walls can release great energy, generate gravitational waves, and reset the pattern of fields that give particles their properties. Such a transition could in principle have helped start a hot dense state after a period of accelerated expansion. He keeps this picture close because it offers both dynamics and a mechanism for ending the acceleration. Yet he does not ignore the shadow this casts on the present. If the vacuum today is also a false minimum, an unimaginably rare tunneling event could someday reset the laws by changing the vacuum expectation values that set particle masses and couplings. The wall of such a bubble would sweep through space too quickly to outrun converting the old vacuum into a new phase with different rules. The calculated lifetimes in simple estimates are vastly longer than the current age of the universe, but the mere possibility turns vacuum into an actor with a plot. He returns to known transitions that altered the vacuum in the early universe. Quantum chromodynamics confines quarks inside hadrons at temperatures below a critical scale, and the change in degrees of freedom modifies the equation of state of the plasma. The electroweak symmetry hides when the Higgs field settles into a non-zero value throughout space, changing the masses of carriers and matter. These transitions appear in the simplest reading to have been smooth crossovers, rather than dramatic first-order events in which bubbles nucleate and crash, but small extensions of the field content can sharpen them into true phase changes. If any of these transitions were strong and first-order, they would have stirred the plasma-generated turbulence and magnetic fields, and launched a background of gravitational waves with a characteristic peak frequency determined by the temperature and the dynamics of the bubble collisions. Space-based interferometers planned for the future would be sensitive to some of this territory, so the vacuum's changing shape could leave audible fossils. He weighs the possibility that the present acceleration is not a strict constant, but evolves slowly with time, a notion called dynamical dark energy, when framed as a field that drifts on a shallow potential. Observations of supernova of baryon, acoustic oscillations, and of the growth rate of structure have probed this possibility, and so far prefer a constant value, but the allowed room for gentle evolution remains. The distinction matters because a true constant invites the unsolved accounting of why its value is so small yet not zero, while a field that evolves raises the question of why it moves so slowly, and why its energy now is comparable to the energy in matter in this particular cosmic era. He recognizes this coincidence as another riddle, as if the vacuum adjusted its pressure to become important, just as galaxies became mature. Some suggest that this near equality is a selection effect in a larger ensemble of regions with different vacuum energies, because complex structures only form in those places where vacuum energy turns on late and with a small amplitude. This reasoning borrows from statistical thinking in a landscape of many vacuae, a framework that may arise naturally in theories that try to unite gravity and quantum fields at the highest energies. It is not a satisfying derivation, but it is a way to avoid treating the small value as accidental without principle. He looks again at the Higgs field, whose measured mass and the mass of the top quark place the present vacuum near a boundary between absolute stability and long-lived metastability. The world survives for a time far greater than any practical horizon, but the near criticality suggests that the parameters of the field sit near a ridge. Some see this proximity as a hint of a selection rule, or a deeper constraint, others as a coincidence amplified by attention. In either reading, the vacuum looks poised, neither precarious in a way that would doom complexity, nor deeply locked in a tireless minimum. That poise may itself be a clue. He thinks about vacuum in curved space-time where expansion stretches wavelengths and can create particles from the changing geometry. A constant acceleration like that of a de Sitter phase gives the vacuum a temperature and a horizon, with entropy linking thermodynamics information and geometry. Horizons hide information and carry entropy measured in areas rather than volumes. The vacuum here is not a backdrop but a thermodynamic system whose properties define temperature, entropy, and pressure. If space-time emerges from entanglement of underlying degrees of freedom, as some suggest, then the vacuum's energy and structure are not primitive inputs, but bookkeeping of deeper arrangements. In that view, The cosmological constant problem is not only a number that fails to cancel, but a sign that the ledger is written in the wrong basis. He does not claim to know which of these interpretations is correct. He collects their demands. The vacuum must contain energy dense enough to accelerate the universe today, yet small enough to honor the ancient light and the web of galaxies. It must be stable against decay on timescales far beyond current age, yet responsive enough in the early moments to allow phase changes that set the laws we see. It must be simple enough to be summarized by a constant in the data, and rich enough to have arisen from dynamics that we can test. Nothing that is not empty begins to look like the most versatile ingredient of all, a medium that can drive expansion, give particles their masses hide and reveal symmetries and perhaps carry the code that sparked the first acceleration. He ends this step holding the paradox gently. Emptiness has weight. Vacuum is action. If there was nothing, the first thing that happened may have been a change in the properties of nothing, and that change still moves the sky. He considers the possibility that when the early symmetries of the universe fractured, they left behind scars not in matter, but in the layout of fields that fill space relics so dilute and elusive that only patient maps and long baselines can discover them. The mathematics of symmetry breaking admits topological defect when different patches of the cooling universe choose inequivalent orientations in a field's internal space. Where those patches meet the field cannot be smoothed away without tearing the configuration, and the tear becomes a persistent object. Sheets of mismatch would be domain walls, point-like knots would be monopoles, and line-like threads would be cosmic strings. Domain walls would over-dominate the energy budget if they lasted in abundance, and the observed smoothness and expansion history argue strongly against a surviving network of such sheets. Monopoles predicted by many grand unification schemes would also have been intolerably numerous, without a later episode of rapid expansion to disperse them beyond the observable region. Strings, however, could survive as a sparse network that redshifts with the expansion, and repeatedly intercommutes a word that describes how crossing strings reconnect and shed loops. The loops oscillate, radiate energy, and gradually evaporate while the long strings can span cosmological distances. He looks for ways the sky might betray their presence. A straight string does not attract like a massive rod. It changes geometry by adding a deficit angle, turning space around it into a cone. Light passing on opposite sides of such a string could produce duplicate images of a distant galaxy, with distinct distortions but with no time delay between them, a signature unlike that of ordinary gravitational lenses that curve space through mass. Surveys of galaxies have hunted for pairs with identical spectra and positions suggestive of this effect. A few intriguing candidates have appeared and then faded under scrutiny, and broad population studies constrain any network to be thin with string tensions, below thresholds that would have produced many such pairs. He then listens for what strings would sing. Oscillating loops produce gravitational radiation, with a characteristic spectrum and sharp features called cusps and kinks act as loudspeakers that beam brief, intense bursts. A cosmic string network across cosmic time would fill the universe with a background of gravitational waves stretching over many decades of frequency. The Laser Interferometer, Gravitational Wave Observatory, and its partners listen at high frequencies suited to stellar mass binaries. They can also set limits on rare bursts from cusps, though none have passed the test so far. Pulsar timing arrays, which monitor the arrival times of pulses from millisecond pulses scattered across the sky, listen in the nanohertz band where a background from supermassive black hole binaries is now strongly suggested. If the measured spectrum and angular correlations ultimately reveal features incompatible with that population alone, a contribution from strings could be part of the explanation. Future space interferometers will open the millihertz band where a background from some early phase transitions or from string loops could peak. The shape of the spectrum across these bands matters. Strings tend to produce a broad, nearly scale invariant background, modulated by the loop size distribution, while a first-order phase transition produces a peaked spectrum tied to the temperature of the event. A combined reading can disentangle these sources, especially if rare bursts from cusps are also seen as spikes above the hum. He returns to the oldest light for subtler fingerprints. A moving string crossing the line of sight at the surface, where the cosmic microwave background last scattered, would produce a line step in temperature, a discontinuity across the projected track known as the effect, first described by the observation that strings impart a Doppler-like shift as they wedge a deficit angle through the photon field. In maps with limited resolution, and with galactic dust and instrument noise, such line steps are difficult to pick out. Yet edge detection algorithms applied to full sky data have placed strong bounds on any contribution from strings to the overall pattern. If strings contributed significantly to the formation of structure, the acoustic peaks would be smeared and reweighted in a way not seen. Instead, the data prefer seeds that were laid down coherently before the plasma rang like a drum. This does not forbid strings. It confines them to a supporting role with tension too low to dominate, but still high enough in principle to poke the map with rare faint signatures. He weighs alternatives to strings born of gauge fields broken at extreme energies. Field theories can also host textures, smooth twists in a multiplet that untie and release energy without leaving persistent defects. A collapsing texture in the early universe could imprint a cold or hot patch on the microwave background with a distinctive radial profile. One much discussed cold spot in the southern sky has invited this interpretation, though a chance fluctuation and a line of sight void remain competitive explanations. He keeps the example in mind as a reminder that anomalies can be lead or misdirection, and that every alluring deviation must clear the 3 hurdles of statistical weight independence from foregrounds and compatibility with the rest of the sky. He broadens the canvas to include strings that are not made of familiar fields at all. Theories that try to include gravity within a quantum framework sometimes admit one-dimensional extended objects as the basic excitations. Variants of these objects, if stretched to astronomical scales during early expansion, would behave like cosmic strings, but with altered reconnection probabilities, loop distributions, or coupling to other fields. A reduced probability to reconnect when strings cross would leave more long strings, and therefore a stronger gravitational wave background for the same tension. Extra light fields coupled to the strings could allow radiation in channels other than gravitational waves altering the spectrum and the allowed parameter space. Bounds on the string tension expressed in a dimensionless product of Newton constant, and tension then depend on these microphysical choices, but in nearly all versions the combination must be smaller than a few times 10 to the -7, or tighter, lest the sky would already have revealed the network in lenses or in the oldest light. He notes how every null result refines not only the possible existence of defects, but also the early history of symmetry breaking. A strong first-order transition at high scale that produces a network of strings would leave gravitational fossils within reach of the next generation of observatories if the tension is near the edge of current limits. A smooth crossover would leave weaker traces. If strings are absent altogether, then symmetry breaking either did not occur in a way that permits them, or inflation stretched their density to a level beyond any practical reach. Each outcome informs the script that wrote the laws. He imagines pairing maps across messengers to pry the door wider. A survey that finds an unusual pair of galaxies with identical spectra and no time delay might be cross-checked with deep, high-resolution microwave data to look for a matching linear step in temperature along the predicted trajectory, and with polarization maps to seek a subtle phase slip. A claimed cusp burst in a gravitational wave detector might be accompanied by a faint, nearly simultaneous radio signature if the string couples to hidden sector fields that convert power into electromagnetism, though such couplings are speculative. A nanohertz background whose amplitude is too high for supermassive black hole binaries alone might be tested against the merger rates inferred from galaxy surveys and from the counts of active galactic nuclei. The point is not to multiply possibilities beyond reason, but to tie each to a practical plan by which a network of instruments can force a choice. He pauses over the aesthetic of scars. The visible universe is smooth on the larger scales with small, well-measured ripples that grow into the web. It would be fitting in a way if a few straight, persistent threads still stitched through that fabric, too faint to guide the whole pattern, yet strong enough to tell him that the loom was once under tension. If there was nothing, and then there was a sudden choice among many symmetrical possibilities, the sites where the choice could not be made consistently would be the honest record of that moment. Strings and their kin would be those records, their rarity, a sign that the choice favoured uniformity, their endurance a sign that the choice was real. He ends the step acknowledging the discipline that the sky has already imposed. The oldest light shows no loud sawtooth edges, galaxy catalogues show no armies of identical pairs, and the high-frequency observatories hear no shower of sharp bursts. Pulsar timing arrays hear a hum most naturally sung by giant black holes. Yet limits are not absences. They are contours on a map that point toward places where discovery still fits. A network thinner by another order of magnitude could still fill the universe with the murmur in the millihertz band, a target for a fleet of spacecraft to test. A single convincing lensing event without delay could still be waiting among the billions of sources that future surveys will image. The scars, if they exist, are faint. Their promise is that faintness is not nothing. It is the precise amount of something that a nearly perfect beginning would have left behind. He entertains a reversal of the usual tale, a picture in which the apparent beginning is not a beginning at all, but a turn-a-rebound from a prior phase that ran in the opposite direction. In such accounts, the universe does not spring from a singular point where densities diverge and time stops. It contracts, slows, and then bounces into expansion. The promise of a bounce is clear. It can explain why distant regions share the same temperature without invoking a burst of early acceleration. Because during a long contraction, light has time to travel and mix conditions across vast stretches before the rebound. It can explain why space looks nearly flat, because certain kinds of contraction dilute curvature and smooth irregularities. He does not accept promises without payment and follows the costs. A contracting universe is vulnerable to anisotropy, the tendency of different directions to behave differently. Left unchecked, anisotropy grows faster than simple matter and threatens to turn contraction into a chaotic, oscillatory state where shear dominates. To tame this one version of the bounce employs an ekpyrotic phase, a contraction where the pressure is enormous compared to the energy density, giving an equation of state much larger than 1. In that regime, anisotropy decays relative to the stiff background, and the contraction becomes smooth and controlled. The price is that the simplest ekpyrotic contraction generates fluctuations that are too blue, with too much power on small scales, and too little on large, the reverse of what the sky displays. The fix is to add more structure, often a second field, whose fluctuations convert into curvature perturbations with the desired nearly scale-free shape. Another price is the bounce itself. To pass from contraction to expansion, the universe must violate conditions that normally forbid such a turn in classical general relativity, or it must invoke a quantum regime where space-time does not behave like a smooth manifold. Model builders explore two roads. In one, effective fields with unusual kinetic terms or with ghost condensate behavior violate the usual energy conditions for a brief interval, yet avoid catastrophic instabilities. In the other, space-time emerges from a quantized geometry whose discrete nature forbids singular collapse, and a bounce arises from repulsive quantum corrections when densities approach a critical value. Both roads offer toy worlds that can be computed and in which fluctuations can be followed across the bounce with matching conditions that preserve continuity and causality. Both roads also raise questions about completeness and consistency when they touch the physics we know at ordinary energies. He watches the ekpyrotic story in its broader frame. It was born in a picture with brains extended objects moving in an extra dimension that approach and collide. The approach corresponds to contraction, the collision heats, and populates the universe with matter and radiation, and the separation corresponds to expansion. In such a setting, the smoothing and the generation of nearly scale-free fluctuations can be arranged with careful choices of potentials and couplings between fields that track the brane separation and those that carry entropy perturbations. Each choice carries potential signatures. The generated fluctuations may be accompanied by a distinctive kind of non-Gaussianity, with a shape that differs from the faint, nearly Gaussian imprint favoured by the oldest light. The gravitational waves produced in these scenarios are often small at the larger scales, implying an almost vanishing curl pattern in the cosmic microwave background polarization, a feature that some future instruments could confirm decisively if a continued silence persists. A matter bounce offers a different path. Here contraction is dominated by a pressureless fluid, and quantum fluctuations exit the shrinking horizon during contraction and re-enter after the bounce with a nearly scale invariant spectrum. This picture also faces the growth of anisotropy and requires a mechanism to mediate the turn without pathologies. It tends to produce a blue spectrum of gravitational waves as a byproduct, which is interesting because it is unlike the slightly red tilt expected from simple inflationary potentials. A blue spectrum would remain small on the larger scales probed by the cosmic microwave background, yet could rise at the higher frequencies that future space-based interferometers monitor. If such a pattern were found, it would be a fingerprint of a contracting past. He then considers cycles. A cyclic cosmos repeats stages of smoothing, heating, clumping, cooling, and renewed smoothing. One scheme uses ekpyrotic contraction to erase memory and a bounce to restart expansion, with a period far longer than the age of the present expansion. Another scheme argues that the far future of an accelerated universe emptied and cooled can be rescaled and repurposed as the next beginning, with a conformal structure of space-time matching the end of one aeon to the start of another. Each cyclic picture must wrestle with entropy. In a world where entropy tends to increase cycles, risk accumulating disorder that would blur structures in later rounds. Strategies to avoid this include the enormous dilution that eternal accelerated expansion provides between cycles, which can spread entropy so thin that a local patch looks pristine again, and the claim that rescaling the end state resets the thermodynamic bookkeeping. He reads these strategies as imaginative routes around the Tolman dilemma, and asks what they would leave that he could test. The ekpyrotic cycles predict no large background of primordial gravitational waves in the microwave bands, perhaps small specific kinds of non-Gaussian features in the oldest light, and a set of isocurvature perturbations that must be converted with care to avoid spoiling the nearly adiabatic character of the observed fluctuations. The conformal cycles suggest that rare giant events in a late aeon, like mergers of supermassive black holes, might leave imprints as circles of low variance in the oldest light of the next aeon. Claims of such circles have been announced and debated without consensus, a reminder that the sky can tempt, and that statistical caveats are not ornaments, but load-bearing beams. He asks how a bounce would treat the arrow of time. If entropy grows monotonically within an aeon, then cycles must be separated by eras that dilute or reset entropy, or the arrow must be understood as local within each cycle, while a larger, more subtle bookkeeping applies across aeons. He returns to the low entropy of the earlier smooth state, and wonders whether the bounce provides the law that chooses that state by attracting the universe toward a set of conditions that are stable under repeated contraction and expansion. He frames this as a possibility rather than a verdict. He does not lean on metaphysical comfort, he leans on predictions. Bouncing and cyclic models can be judged by their forecasts for the shape of the power spectrum at the largest scales, for the presence or absence of primordial curl in polarization, for specific forms of non-Gaussianity, and isocurvature for blue or broken spectra of gravitational waves, and for relic defects or features that originate in repeated symmetry breaking. They can also be judged by their ability to support a graceful reheating that fills space with a correct mixture of radiation and matter, without leaving too many unwanted relics, by their capacity to avoid instabilities during the bounce, and by their treatment of quantum fluctuations, so that the classical world emerges cleanly in the expanding phase. He watches the data converge. The oldest light carries a nearly perfect, slightly tilted spectrum with tiny deviations from Gaussian behavior. It shows no firm evidence of isocurvature, and it places tight limits on a primordial curl that would have been large had early acceleration occurred at very high energy. Pulsar timing arrays reveal a hum most likely from giant black hole binaries, but they also set a stage on which a blue spectrum from a bounce could later rise. Space interferometers, when they fly, will add another octave. Galaxy surveys measure the growth of structure with increasing precision, and any departure from the expected pattern caused by remnants of a contracting phase would become progressively hard to hide. He ends the step with a fair reckoning. A bounce is not a refuge from difficulty, it is a shift in difficulty. It replaces the challenge of explaining what sparked early acceleration with the challenge of constructing a stable turn and a smoothing contraction. It replaces one set of telltale fossils with another set that are still in play. It opens the door to a universe without a singular start, but it asks him to accept that what looks like a beginning is a page in a longer book. If there was nothing, then in this story there was never quite nothing. Only the quiet between movements with a theme that returns altered by what it has passed through. Whether the present movement carries faint echoes from an earlier one is a question that the sky can answer, and he already knows where to listen. He considers a landscape rather than a single garden, a picture in which the universe is not one region with one set of numbers, but a patchwork of regions, each with its own recipe for masses, couplings, and the strength of vacuum energy. Eternal inflation supplies the stitching that sews this quilt. If the field that drives early accelerated expansion decays slowly and is buffeted by quantum fluctuations, some patches finish their sprint and reheat, while other patches fluctuate back up the slope and continue to inflate. Those inflating zones spawn more zones in an endless cascade, and wherever the field settles into one of many possible valleys, a pocket with specific low-energy laws is born. He sees how this picture is less an extra adornment than a generic consequence of a gentle engine perturbed by quantum noise. He also sees why it feels like a philosophical gamble. If many pockets exist beyond the horizon, direct travel to compare them is impossible. He does not abandon the idea for that reason alone, because physics often infers unseen structures from the consistency of the scene. He asks what would make such a landscape earn its keep. One service it offers is a translation of coincidence into statistical accounting. Several numbers in the world look uncannily small or delicately balanced. The vacuum energy density is tiny compared to natural estimates. If it were much larger and positive accelerated expansion would begin so early that structures could not form, and if it were much larger and negative collapse would arrive before galaxies had time to grow. The mass of the Higgs field sits near a boundary where quantum corrections threaten to push it higher. If it were much heavier, the spectrum of particles and nuclei that chemistry needs might be altered beyond recognition. The strength of primordial ripples is small. If larger, the universe would clump into black holes and short-lived stars before complexity could breathe. In a single universe with fixed laws, these delicacies press him to hunt for protective symmetries or deep principles that fix the values. In a landscape, these numbers can scan from place to place, and observers arise only in regions where the values land in the narrow ranges that permit long-lived structure. Selection then converts improbability into typicality under a conditional rule. Given that observers exist, what values should they expect to measure in a wide ensemble? He knows this reasoning is not a free pass. It demands a measure, a way to assign weights to different pockets, so that typicality has meaning. Here he enters the thicket called the measure problem. In eternal inflation, every pocket type that is possible occurs infinitely many times. To compare infinities, one must regulate, and different regulators privilege different outcomes. A cutoff in proper time tends to overweight the youngest pockets, and runs into a youngness paradox that favours worlds inconsistent with observation. A cutoff based on the scale factor, or on the light cone patch, avoids some pitfalls, but not all. Causal diamond measures and stationary measures attempt to capture the view of a single world line or the late-time attractor behavior. Each approach shifts statistical predictions and changes how rare freak observers compete with ordinary histories. He does not pretend that the measure is settled. He reads the situation as an active ledger, where a better regulator must be justified by first principles or by coherence with tests. He looks for those tests. Bubble collisions between neighbouring pockets could leave circles of unusual temperature or polarization in the oldest light disks cut from the sky by an encounter that perturbs the last scattering surface. Searchers have looked for such concentric features, for special alignments, and for phase shifts beyond the standard drumbeat of acoustic peaks. None have cleared the highest bars of significance and robustness, yet the kinds of signatures are specific enough that negative results already bound how often collisions could have occurred near our past light cone. He considers the possibility of tiny spatial variations in what should be constants. If the fine structure constant or the ratio of electron to proton mass drifted across space, because our pocket rests in a field that is not quite stationary, distant absorption lines in quasar spectra could show shifts that do not fit a single number. Claims of such drifts have been debated and remain unsettled, but the method is clear, and new instruments with steady calibration improve the reach. He weighs another root population predictions. In a landscape where parameters scan, one can ask what fraction of pockets produce galaxies of a certain type, or a cosmic expansion rate of a certain value. If the answer yields a distribution peaked near what we measure, the landscape gains plausibility. There are attempts to compute such distributions for the vacuum energy, by counting how often regions land in valleys of different depths, and they suggest that values near the threshold that allows galaxies should be typical under mild assumptions. He takes comfort and caution from this. Comfort because it shows that a selection effect can naturally single out a small number without a precise mechanism. Caution because the computation depends on an assumed measure, and on how one weights observables by the number of observers, a quantity that is itself slippery. He examines the idea that high-energy theories produce a vast tableau of possible low-energy worlds. Approaches that attempt to unify gravity with quantum fields often admit many metastable vacua, each with different shapes for fields, different topologies for extra dimensions if such exist, and different values for coupling constants. Fluxes wrapped on hidden cycles can discretely adjust energy densities, creating a near continuum of options. In such a case, a landscape is not a literary flourish. It is the practical consequence of an enormous configuration space. The hope is that cosmological dynamics during eternal inflation samples this space and populates it with pockets, some of which look like ours. The challenge is that the space is so large that making robust statistical predictions is hard, and the hope risks becoming a label attached to our ignorance. He does not let that risk turn this into a story without content. He asks for constraints that must hold in any patch where observers can arise regardless of the larger ensemble. Cooling must permit stable nuclei with multiple protons to exist. Carbon burning and oxygen synthesis in stars must not be spoiled by small shifts in resonance levels. The matter-power spectrum must be shaped so that galaxies form before vacuum energy dominates. The amplitude of fluctuations must be small enough to avoid early collapse, yet large enough to seed structure before baryons lose their chance. These anthropic constraints a term he uses sparingly and without romance are not arbitrary. They are the minimal conditions for organized complexity to persist. He notes that our universe sits near critical lines in several of these conditions. It is tempting to see this as evidence of selection in a landscape, and equally tempting to suspect that deeper laws set the values for reasons yet to be derived. He balances both temptations by keeping to predictions that cannot be tuned away. If the curl pattern in the oldest light remains absent at a level that condemns many simple inflationary potentials, models that naturally lead to eternal inflation but predict small curls will be preferred. If space-based interferometers hear a background of gravitational waves with features matching a first-order transition at energy scales below the highest unification thresholds that would favor landscapes in which multiple phase changes occur as fields settle. If improved quasar spectra and laboratory clocks find no spatial or temporal drifts in constants across larger baselines, landscapes in which light fields roam at late times would be constrained. If instead small coherent drifts appear, then the patchwork will have written on the sky with a firm hand. He returns to the human weight of this idea. A multiverse can feel like a surrender, dissolving unique explanations into a catalogue of elsewhere. He does not read it that way. It is a hypothesis that moves the burden of explanation to distribution rather than selection to dynamics over principle, and it is only as strong as its ability to survive contact with maps and clocks. It also sharpens the question that began this journey. If there was nothing, what selected the first spark? In a landscape, perhaps nothing selected in the sense of design. Quantum noise and vacuum structure did, and the values we see are those that permit stories to unfold. Yet even that answer appeals to a deeper regularity, a law for fields, for vacua, for tunneling rates, and for how inflating regions reproduce. He ends this step by conceding both the allure and the austerity of the patchwork. Coincidence begins to look curated, but the curator is the distribution, not a hand. The price of this curation is a measure that must be earned a checklist of signatures, that must be chased, and an acceptance that typicality can be as sharp a tool as symmetry when used with care. If that price is paid, the spark may turn out to be an event not of cosmic fiat, but of statistical inevitability, one small ignition among many and notable only because it happened in a place where memory could take root. He entertains the thought that black shadows may have gathered before the first lanterns were lit, that some black holes were born not from dying stars but from the density of the newborn universe itself. These are called primordial black holes, and they could form when exceptional overdense regions re-enter the causal horizon after a phase of early expansion crossing a threshold where pressure cannot resist gravity, and collapse proceeds at nearly the speed that light sets. The mass of such a collapse is tied to the horizon mass at that moment, so a spectrum of initial masses is possible, from less than a mountain to more than 1,000 suns, depending on when the fluctuations grew large. He asks what could amplify selected scales to that threshold. A brief pause or turn in the early expansion could boost power over a narrow range of wavelengths. A temporary change in the speed at which ripples propagate could sharpen features. A phase transition near the epoch when quarks confine into hadrons changes the pressure and lowers the barrier to collapse, favouring solar mass scales. In all such tales, collapse does not happen everywhere. It happens rarely and stochastically, leaving islands of extreme density that later drift through a sea of ordinary matter and dark matter. He takes an inventory of what these ancient shadows would do, and how the sky could betray them. If the initial masses are very small, less than an asteroid, quantum radiation described by Hawking slowly evaporates them. The rate accelerates as the mass decreases, ending in a flash of high-energy quanta. The observed gamma-ray background seen by space telescopes, along with the absence of local bursts at the expected energies rules, out large populations of the lightest primordial black holes. At somewhat larger masses that survive to the present, gravitational microlensing becomes a test. A compact object that wanders across the line of sight to a star temporarily brightens the star by bending its light. Surveys with vigilant cadence have watched millions of stars in the Magellanic Clouds and toward the bulge of the Milky Way, and their tallies show that compact objects between a fraction of a solar mass and a few solar masses cannot make up more than a small fraction of the dark matter. A different camera on the Subaru telescope has stared at distant galaxies to catch microlensing events on shorter timescales, squeezing windows around lunar-to-Earth masses. Quasar light curves split by lensing offer another route. If many compact objects sat in the lensing galaxies, they would add flicker to the images that is not observed at the required level. Each of these methods narrows corridors where primordial black holes can still hide in abundance. He then turns to a surprise that reopened interest: the laser interferometer. Gravitational Wave Observatory, joined by sister detectors in Europe and Japan, has heard many mergers of black holes with masses around 10 to 50 suns, sometimes larger. Stellar evolution can make such pairs in special environments, but some of the early events carried low spins and mass ratios that invited a speculative reading. Perhaps some are primordial, formed in the early universe, paired by chance in the expanding medium, and driven together by gravity over billions of years. If that were the case, the distribution of masses, spins, eccentricities, and redshifts would differ subtly from those of black holes born in stellar clusters or in isolated binary star systems. The rate would rise toward earlier times in a way set by the initial clustering of the primordial population, rather than by stellar formation history. The background of unresolved mergers would produce a hum whose amplitude and slope would carry the imprint of ancient initial conditions. He watches as catalogues grow and models sharpen. Some features look friendly to stellar origins, others leave a slender lane for an admixture of primordial sources. Nothing compels the early universe channel, but nothing yet seals it away for all time. He considers heavier seeds. Quasars illuminate the young cosmos only a few 100 million years after the first light lifts, and some harbour black holes of more than 1 billion solar masses. Growing such giants from the corpses of the first stars is difficult under ordinary conditions because radiation pressure fights accretion, and the time available is short. Primordial black holes born with hundreds or thousands of solar masses would ease the ascent, seeding the centres of forming galaxies with a head start. Yet heavy primordial seeds would also disturb their surroundings. Their growth by swallowing gas in the Dark Ages would heat and ionize the medium, altering the timing and character of reionization. Their X-ray and ultraviolet output would modify the 21 centimeter signature from neutral hydrogen, changing the depth and shape of any absorption feature in ways that radio arrays can test. The absence of strong early heating in current limits sets tight conditions on how abundant such seeds can be and how greedily they can feed. He tracks another lever that the ancient shadows would pull the delicate pattern of the cosmic microwave background. Black holes that accrete during the era after recombination would inject energy into the gas, slightly changing the ionization fraction and blurring the small-scale anisotropies of the oldest light. The data from the Planck satellite bound this effect, translating into limits on the product of abundance and accretion efficiency for a wide mass range. He adds dynamical tests closer to home. A halo made of compact masses would heat stellar disks and puff them up beyond what is seen would perturb wide stellar binaries in ways astronomers can count and would alter the internal motions of the faintest dwarf galaxies. These arguments, too, exclude large swathes of parameter space for primordial black holes as the dominant dark matter. Yet the exclusions are not monolithic. A narrow band of asteroid to lunar masses and a slender region around a few tens of solar masses remain as partially open doors subject to astrophysical uncertainties and to model choices about accretion clustering and mass spectra. He thinks about production in sharper detail. Collapse near threshold is not a step function. Critical phenomena amplify the diversity of outcomes, producing a mass function that often resembles a log-normal shape, even if the initial spectrum is narrow. If some physics in the earliest expansion transiently boosts power on a specific scale, a peak distribution of primordial black hole masses follows rather than a wide smooth one. This matters because constraints vary strongly with mass. A carefully shaped peak can avoid the harshest bounds while delivering enough objects to accomplish a modest role, such as seeding some supermassive black holes or providing a subdominant fraction of the dark matter that still leaves fingerprints in gravitational waves. The same early boost that enables collapse would also create a flood of gravitational waves when the enhanced fluctuations re-enter the horizon and stir the plasma. That radiation generated secondarily by the large inhomogeneities would form a background with a peak frequency linked to the mass scale of the primordial black holes. Pulsar timing arrays and later space-based interferometers could hear such a background and separate it from other sources through its shape. Discovery of that background with a matching mass peak in merger events would trace a line straight back to a feature in the earliest ripples. He allows a daring thought that connects absence with presence. If dark matter is not made of new particles beyond the familiar field content, and if a careful accounting of constraints still leaves small islands where primordial black holes can live, then a hybrid picture may be true. Most of the invisible mass is cold and diffuse, as measured by many surveys, while a tiny but influential share consists of ancient compact objects that seed stir or signal at key moments. Such a mixture would be messy enough to match the complexity of galaxies and clean enough to satisfy the oldest light. It would honour the firmness of the dark matter paradigm while admitting that gravity can do odd work when conditions allow. He ends the step with an image that suits the theme. Lanterns arrive late, forged by nuclear fire in stellar cores. Before them, the night may already be populated by shadows cast by nothing more than the first fluctuations. Those shadows would not glow, they would bend heat and hum. They would tilt the pattern of the sky with tiny lensing events. They would murmur through the timing of pulsar clocks. They would tug at the growth of small halos, and they would inch the parameters that describe the oldest light. If a convincing signature appears, it will not be a single shout but a chord, a microlensing curve with a right timescale, a merger population with telltale spins and eccentricities, a background of gravitational waves with a peak that points to a specific birth scale, and a quiet, consistent accounting that the rest of the universe still fits. If there was nothing, these black holes would be among the first something shadows that gathered before the lanterns were lit, teaching him that darkness too can be a way to begin. He reframes the problem of beginnings as a problem of description, asking how many bits it takes to specify a universe like this one, and whether the first state is best understood not as a pile of particles, but as a short program that generates a long, richly structured output. In this view, the smoothness of the early cosmos, the near-scale free ripples the almost vanishing curvature, and the small handful of parameters that fix the recipe for light and structure are not just dynamical facts. They are signs of compressibility. A compressible object is one that can be written with fewer symbols than its length, by exploiting regularities and symmetries. The more symmetry, the shorter the code. He looks at the oldest light and sees a map whose bulk can be summarized by a compact set of numbers that describe the heights and positions of acoustic peaks, a tilt just shy of perfect neutrality, and an amplitude small enough to keep the later universe gentle. He looks at the inventory of matter and energy and sees a ledger that needs only a few entries. Dark energy, nearly constant cold, dark matter, frictionless, and slow, baryons in a modest fraction, and neutrinos light but not weightless. He looks at geometry and sees flatness within current precision. None of this reads like a random draw from an extravagant space. It reads like a dataset with low algorithmic complexity. He does not mistake this for proof that reality is literally a computation on a classical machine. He uses the language of compression as a guide to what physical principles could favour, short descriptions, symmetries that force relations among couplings, renormalization flows that erase many microscopic details and leave only a few relevant parameters. At large scales, attractors in dynamical systems that pull diverse initial conditions into narrow bands of behaviour. Inflation presents itself again as a compressor stretching space so broadly that any initial bumps are ironed thin, while quantum fluctuations supply a minimal seed pattern with simple statistics. A bounce with an ekpyrotic phase presents itself as a different kind of compressor damping anisotropy and curvature, so that a wide class of contracting histories feed the same expanding script. He connects compression to information bounds written on geometry. A black hole does not store information in its volume but in its horizon area, measured in squared lengths of the smallest meaningful scale, and the maximum entropy in a region is then proportional to the area that encloses it, not the space inside. This is the holographic principle, a conjecture sharpened in precise dualities, in which a theory with gravity in a volume is equivalent to a theory without gravity on its boundary. He reads these relations as a deep constraint on how many degrees of freedom a region can carry, and on how information and geometry intertwine. If space-time emerges from patterns of quantum entanglement among underlying degrees of freedom, as several lines of reasoning suggest, then the first state of the universe may be special, because its entanglement structure is special, minimal in its gravitational sector, precise in its correlations across large scales, and simple enough that a small code can write it. He considers entanglement as the mortar of geometry. In toy models, stitching together many quantum systems with the right pattern of entanglement generates an effective space in which distances are measures of shared information while disentangling tiers space apart. In that language, the early universe has almost uniform, coherent, long-range entanglement that leaves only the faintest ripples. As the universe evolves, interactions and clumping generate finer and finer partitions of information, and the arrow of time reads as growth in the complexity of entanglement that cannot easily be undone. The low gravitational entropy at the start then becomes the statement that the initial code specified geometry, with almost vanishing tidal distortions and minimal hidden information behind horizons, a pattern that required very few bits to draw. He folds this into the practice of science, which already prizes short codes through Bayesian model comparison and the informal rule called Occam's razor. Given two explanations that fit the data, the one that uses fewer adjustable numbers or invokes fewer unlikely coincidences is preferred. The power spectrum of the oldest light is fit by a model with a small set of parameters that extrapolates across many orders of magnitude in scale. The success of that fit is not only a victory of dynamics, it is also a statement that the cosmos is describable by a low-dimensional family, which is what short codes look like in statistical dress. He asks whether this style of reasoning can do more than celebrate simplicity. It can propose constraints a plausible beginning should be reachable by a rule that compresses, not by an inventory that explodes. A natural scenario is one that lands on an attractor without painstaking aim, one in which the basin of attraction is broad. It can reorder riddles. The smallness of vacuum energy may be a symptom that the true variables are not the naive sums of zero-point modes, but the data of an emergent description in which that sum is already cancelled or sequestered by a deeper conservation. It can organize speculations. If spacetime is born from entanglement, then the initial state may be close to a code state, a pattern stabilized by error correction that resists small perturbations and thus explains why early uniformity survives quantum noise. In such pictures, locality itself is a derived property of the code, and the first spark is the moment a particular error correcting pattern condenses from a higher energy phase. He turns this into possible contact with observation. Holographic bounds limit the amount of independent structure that a patch of the early sky could carry, and any theory that asks for more should be suspect. Measures of long-range entanglement may be mirrored in specific higher-order correlations among the ripples in the oldest light's subtle shapes in the statistics that go beyond the simple bell curve. The near absence of such shapes so far suggests that the code at the beginning was close to Gaussian, which in quantum field language is the simplest, most compressible state consistent with the rules. If future maps were to find a particular pattern of non-Gaussianity, for example, one that links 3 or 4 points in a shape that implies a preferred coupling among modes, it would tell him that the code had a subroutine beyond the minimal seed. Gravitational wave fossils are another channel. A loud background would imply a large energy scale and perhaps a more baroque engine. A quiet background keeps the code short. Even the peculiar alignments and low power at the larger scales can be read as hints that the code includes boundary conditions or global modes that a pure random draw would not supply, and their persistence or demise with better maps will favor one compact description over another. He considers the ethical temptation to overuse the metaphor. A universe is not a text file zipped by an algorithm and a principle of minimal description. Length is not a law of nature unless a theory explains why. He keeps the metaphor honest by treating it as a reflection of symmetry's attractors and entanglement structures that real equations can implement. Symmetry breaking becomes the moment the code expands, adding lines that multiply possibilities, while preserving the few rules that anchor everything. The low entropy start becomes the short header at the top of the file. The later richness becomes the long body generated by repeated application of simple transformations. Seen this way, nothingness becomes the empty string, and the spark is the first symbol plus the rule for iteration. He ends the step by turning the question back to its root. If there was nothing, what wrote the first line? Perhaps the first line is not written but selected by stability in a space of possible codes, the only pattern that generates a geometry with small curvature and a spectrum of ripples that allows chemistry and memory. Perhaps the first line is inevitable once one demands that information bounds are respected and that entanglement be as uniform as possible across the wider scales. Perhaps the first line is still hidden inside a theory that unites quantum mechanics and gravity so tightly that geometry and information never separate. Whatever the truth, the habit of compression has already guided him toward the clues that matter: the smallness and simplicity of the parameters, the coherence of the earliest map, the economy of successful models, and the deepening suspicion that the universe is written in fewer words than its size would suggest. He gathers the clues on one long table and asks the only question that still matters, given this map of uniform light with tiny ripples, this near-flat geometry, this quiet limit on primordial gravitational waves, this arrow of time that starts in a state of astonishing gravitational order, this slight excess of matter over antimatter, and this late acceleration driven by energy in the vacuum, what could have lit the first spark? One path begins with a fluctuation in a pre-existing vacuum, a quantum tremor that lifts a small patch over a barrier and sets a field rolling down a gentle slope. In that picture, the patch inflates, smooths, and stretches. Quantum jitters intercedes, then decays into a hot, dense plasma that begins the expansion we call our beginning. The spark is a tunneling event, rare but magnified by exponential growth. This tale is technically clean and rooted in calculations that have already survived many tests, yet it shifts the burden to the nature of the vacuum it arose from, to the measure that tells how often such patches appear, and to the reason that the potential energy landscape has the right shape. Another path reframes the spark as a phase change in a more encompassing structure, a transition not in a single scalar field, but in the very way geometry and information are organized. If space-time emerges from patterns of quantum entanglement, then a condensation of a particular error-correcting code could be the move from an undifferentiated pregeometric stew to a smooth manifold with small Gaussian ripples. The spark here is a change in entanglement that compacts the description, pulling the system onto an attractor where curvature is nearly zero and fluctuations are as simple as possible. This picture honors the low algorithmic complexity of the initial state and the holographic limits on information, but it waits on a full theory that derives dynamics from entanglement in a way that reproduces all known fields and interactions. A third path revisits the possibility that what looks like the first page is the middle of the book. A contracting world smooths through an ekpyrotic phase, then bounces into expansion, without singularities, perhaps through a quantum regime where geometry is discrete, or where effective fields briefly violate familiar energy conditions. The spark is a turn rather than a birth, and the initial smoothness is a consequence of the long contraction that came before. This path draws elegance from reversing the horizon riddle and from replacing the demand for a special start with the dynamics of an attractor, but it must arrange the bounce without instabilities, pass fluctuations cleanly through the turn, and agree with the near Gaussian sky while leaving at least one unique fossil to prove it true. A fourth path accepts a cosmic patchwork. Eternal inflation generates many pockets with many low-energy laws, and our values are the ones that allow chemistry and memory. The spark is not unique. It is typical under a conditional rule that weights regions by their capacity to host complex structures. This path has already paid one bill by explaining why vacuum energy can be tiny without a delicate cancellation, and why several numbers perch near critical boundaries, but it leaves the account in arrears until a principled measure and clear signatures of collisions, drifts of constants or special patterns confirm that the patchwork is more than a graceful dodge. He does not choose among these paths by taste. He asks what any spark must accomplish. It must deliver a horizon in which distant regions once shared information, so that the oldest light is uniform to parts in 100,000. It must flatten curvature to a level below current sensitivity. It must plant nearly scale-free, nearly Gaussian adiabatic fluctuations with a slight red tilt. It must avoid pouring in strong isocurvature modes. It must not leave long-lived defects in numbers that the maps have ruled out. It must provide conditions for a small matter excess without erasing it later. It must anchor a low gravitational entropy state that gives the arrow of time a foothold. It must hand the baton to ordinary expansion with a temperature particle content and neutrino census that match the first minutes written in light elements. It must do all this with enough parsimony that the code describing it is short, or else it must explain why a long code could ever be natural. Measured against that list, an inflating patch born by tunneling or quantum rolling is an efficient worker which explains its long tenure at center stage. A bounce is still in the contest if it can keep its promises and leave a blue or broken spectrum of gravitational waves for future detectors to hear. An emergent transition from entanglement to geometry looks increasingly plausible. The more the early map resembles a code state, but it will win only when it derives a specific testable spectrum and a schedule of phase changes that reproduce the ledger of symmetry, breaking baryogenesis and relic counts. A landscape earns its keep if it converts coincidences into population peaks, and if it yields one or two unmistakable signatures, perhaps a population of bubble collision disks drawn onto the oldest light at a level tomorrow's instruments can see or rule out. He then turns the lens inward one more time and frames a composite in which these paths are not rivals, but chapters. An emergent transition writes space-time and its low curvature by organizing entanglement into a code. Within that space-time, a gentle potential carries a field that drives a brief low amplitude inflation that smooths and seeds with minimal noise, leaving gravitational waves too soft for current instruments, but not beyond reach forever. Near the end of that era, couplings set by high-energy symmetries steer a leptoner symmetry that electro-weak processes convert into the baryon excess we inhabit. The vacuum energy that dominates today is not the naive sum of zero-point modes, but a value fixed by constraints in the emergent description, small by necessity rather than by cancellation, and nearly constant because the relevant field is pinned by dynamics rather than by chance. If the potential admits multiple long-lived minima, eternal inflation at very low energy can still populate a patchwork beyond our horizon, but the measure is controlled by the same entanglement architecture that gives geometry a count of degrees of freedom, taming infinities that earlier approaches mishandled. This composite is not a manifesto. It is a scaffold for tests. It asks detectors of microwave polarization to keep listening for a curl that would announce a high spark, or if absent, to pin the spark to a gentler threshold. It asks pulsar timing arrays and future space interferometers to map the spectrum of low-frequency gravitational waves for blue rises or broken shoulders, that a bounce or a peaked primordial power would produce. It asks neutrino observatories and double beta decay experiments to decide whether leptogenesis owns the matter excess. It asks radio arrays to film the dark ages and the dawn of the first stars for any early heating that exotic seeds or decays would cause. It asks spectrographs to track the constancy of constants and underground tanks to watch for proton decay that would bind symmetry, breaking to grand scales. He does not pretend that a single find will write the origin in full. He expects a mosaic, a small curl or a stricter silence, a hum, with a slope that leans blue, a null result that prunes whole forests, a neutrino phase that tilts the balance, a slight drift or a tightened zero, a mist decay that lifts the energy of unification beyond today's dreams. Each tile narrows the spark. Perhaps in the end the spark is not a single event but an emergent necessity, when information organizes just so space appears. When space appears and a field sits high and flat expansion smooths. When it ends, heat and particles fill the page. When symmetries break, small asymmetries write the rest. In that telling, nothing is the wrong word. The right word is before. Before geometry, before clocks, before light, there is a pattern that can be written briefly, and from it the long sentence unfolds.